Well, good morning, everyone. Welcome to Storage Developer Conference 2018. Get this other mic turned off. My name is Michael Aros. I'm the Executive Director for SNIA. Hopefully you can hear me. If not, I have a loud enough voice. Excellent. SNIA, really quick overview and reminder of all the great things that the organization does. We've been around for 21 years now and cover a huge amount of space in the storage domain. From storage management to network storage, looking at the next generation data center technologies and how do you manage it, how do you enable it, power efficiency and measurement, the great work that we do there with Emerald, with SNIA Emerald and the EPA and other organizations around the world. Persistent memory, top of mind for everyone. That's why it's at the top of the tree as well. Physical storage, data management, data security, cloud storage technologies. Very big breadth of things that we cover in being a leader for storage innovation and education around the world. The fundamentals of what SNIA does, really standards, top of the list, what we deliver to the industry. We do plugfest and conformance testing programs for those standards to ensure interoperability amongst vendors for our end users and consumers of those technologies. Technology initiatives, these are really communities that we have that collaborate on how do we educate the industry and raise all boats for new technologies. One of the barriers to entries for new technologies is people understanding them and their value proposition and where they fit. No one thing solves all problems, but when you have a vendor-neutral approach in describing what those technologies, you become a trusted source of that advice of where those technologies fit in the marketplace. The education and certification, we're in process of finalizing a new upper-level certification. We have thousands of people around the world that are SNIA certified, a vendor-neutral certification. A lot of recognition from the industry about this program. And of course, SNIA events. You are at one here today. Thank you for joining us. It's not only just about the presentations you hear today, it's about the relationships, connections, the hallway conversations, and those relationships that are built that solve problems in the industry and deliver faster time-to-market products for your companies and better solutions for the end users. Quick overview, these are a list of the standards that SNIA has released this year in 2018 to date. So SNIA Emerald 3.0.2, LTFS, yes, this is still a technology that is around and emerging, and believe it or not, it's still one of the fastest way to onboard a cloud. Never underestimate the bandwidth of that FedEx truck with a bunch of tapes driving up 101. Real-world storage workloads, looking at how do you actually assess in a standard way or a common way performance across devices and systems. The performance test specification for solid-state storage. Of course, SMI 1.A.3 was released this year as well, a very mature, long-standing spec in the industry for storage management. And the Swordfish Scalable Storage Management API 1.0.6 was also released. In terms of what's in development, a lot of things that SNIA is working on. The Cloud Data Management Interface 2.0 is in flight and to be released in the next year. The reference implementation for CDMI 1.0, SNIA Emerald for Power Efficiency 4.0 is in development right now. And an important part of the work that SNIA has done and in the industry where the vendors came together to define how do you measure, how do you improve on power efficiency and responsibly deliver technologies in the world. This is adopted and used not just in the US by EPA, but across the world in Japan, Europe, and other places. It's important that we've made great progress in this domain. It's important we don't forget about this and the great achievement that we have as an industry where we came together and defined what the measurements and then the improvements should be made rather than having governments dictate what they are and have those not necessarily mesh together with the understanding of the technology, how it's used and deployed. So please continue to invest in this area. It's important that we don't lose track of the great success we've had here and start to deviate. LTFS 3.0, it's in progress. The NVM programming model 1.3, object drive key value API specifications, the Swordfish Scalable Management API 1.1, and of course on security, the TLS version 1.1. About 2 years ago, we had another group that joined SNIA, the SFF group. This group looks at form factors and transceivers and connectors. As you can see, these are the specs that they've released this year alone. Extremely active group, over 60 members. They've grown significantly by about 50% since they've joined SNIA. Please pay attention to this space. We can't forget about the nuts and bolts and how the technology that we develop actually gets physically delivered in the world. And this is one of the key places where those standards are developed and agreed upon in the industry. Upcoming events, just want to remind you about a couple of things. October 11th, we have the SNIA annual members meeting. This is a 45-minute call where the chairman of the board, treasurer, and myself give you an update as to what SNIA has been doing in the last year. You've gotten a short preview of just the technology that we've been working on. There's a lot more that SNIA does we'll cover in that call, including our financial health and our plans for 2019 and the future. So please join us for that, particularly if you are a voting member in SNIA, so we can take care of the corporate business as well at that call. The SNIA Annual Members Symposium in January 21st to 25th, right back here at this hotel. We've moved it from the Westin in Santa Clara to this location because we are growing, needed more space, including for the Persistent Memory Summit. So the symposium, it's your opportunity both as members and as non-members to join SNIA and find out where things stand in terms of the technical work that the work groups are delivering, find out the latest update and interact with the leaders of the organization, both the board and the technical council that participate at that event. Also, not on here, but if you are in Colorado Springs in 2 weeks, that is another symposium that we have there annually that, again, technical work groups are working on various things, including on the Tuesday of that week, we will have another working session on what was a very successful Birds of a Feather session last night on computational storage. So please put that on your calendars. The Storage Developer Conference for next year, back here at this hotel, September 23rd to 26th. Put it on your calendars. September, it's a very busy month in the industry, and we want to make sure that you knew the next event when it's scheduled. Now, SNIA is not just in the US. It's been international for 3 years now, but it's gone even more international this year in particular. We added SDC in EMEA in Tel Aviv, very successful event. Over 100 people attended for a first time event in February this year. The date for next year is set for January 30th. And exciting news around that as well for those that are familiar with the SMB3 conference, Plugfest downstairs. For the very first time, that Plugfest will actually be in Tel Aviv as well that week. So we'll be sending out more announcement and registration on that in the next week or two. But very exciting to see the industry coming around these events and collaborating. India, May 23rd and 24th in Bangalore. This will be the 4th SDC for India. A great community of developers there and passionate storage people that are learning from one another. Right now, this year, they started meetups where they're meeting throughout the year on various topics, using webcasts and educational things that SNIA has put out as primers, and then getting together and having very meaningful conversation about the challenges in the industry and how to move things forward in various domains. A huge thank you to you, the attendees, making this event successful. Also to the speakers who put in a huge amount of time and preparation, delivering valuable content to you and spurring on even more conversations about the next thing that the storage industry should be doing. And last but not least, to our sponsors. Couldn't do it without you. This is what helps keeps the cost of the event reasonable for the attendees and helps us put this program together. Big hand of applause and thank you to the sponsors. Today's schedule at a glance, we'll be kicking off the general sessions here shortly. I'll promise not to go much longer, from 9 to noon. Then lunch on the mezzanine. Please take some time, both during the lunch as well as the network reception, 5 to 7, to go around, look at what our sponsors' tables and information they have, interact with them, ask them questions, give them your feedback. And of course, breakout sessions will continue 1 to 5. Last but not least, after the network reception, please join us for the Birds of a Feather sessions for this evening. I'll cover what those topics are in a second, from 7 to 8 this evening. The Storage Developer Conference mobile app, we've listened to your feedback from last year. We're continuing to make improvements. I know we have more to make from this year, but 321 of you have already downloaded and installed this app. So if you have not downloaded or you're not using it, you're in the minority. Please join the rest of us and download and install it. The various modes you can do there, or search on your app stores for Storage Developer Conference, full spell out to get the application. The SNE SMB3 Plugfest that I mentioned, thank you to our underwriters. Both Microsoft and NetApp have been longtime sponsors and supporter of this Plugfest. And the participants, you can see and recognize the logos on there in terms of the names and the companies that are participating. Again, collaborating with one another, ensuring their products and implementations interoperate and deliver a seamless and good experience for the end users. We do have a SNE Swordfish workshop as well today. I'll give a little bit more information on that. A big thank you to one of the storage communities in SNEA, the SMI Storage Management Initiative, for sponsoring that workshop. Encourage you to attend it. The general session speakers, again, we'll kick it off shortly. We have some great topics. Look forward to, again, your interactive ask questions at the end, provide feedback, and discuss, mingle amongst yourself and with the presenters later today during the breaks, lunch, and networking sessions. The SNEA workshops I mentioned, it'll be an opportunity for you to really interact with demonstrations, learn, dive in at your own pace on SNEA Swordfish and see it for yourself how this new storage management solution is coming to market. We've had several Plugfest for SNEA Swordfish, and we already are starting to see a list of companies and solutions that are coming to market this year and many more next year. So exciting time in the industry, and very interesting developments on how do you increase your efficiencies for managing a growing amount of storage out there. The Birds of a Feather sessions, NVMe BOF and Meetup, it will be happening in parallel with the Open ZFS BOF at 7 tonight, right up here in these in Stevens Creek and Cypress rooms. Please join us for those. It's your opportunity to interact with your fellow industry participants on these topics. Share your thoughts, share your input, share your challenges that you may want the rest of the industry to come around and help solve. We do have a daily $100 gift card that we give for evaluations. We very much value your input, and we depend on those valuations to make changes and improvements to this event to make it more valuable for you. Your time is valuable, and we want to respect that. Let us know what's going well. Let us know what could be improved as well. So with that, yesterday's winner, Benjamin from Dell, congratulations. You can pick up your $100 gift card at the registration desk, and unless you fill out your survey and feedback today, well, you're not eligible for today's, so please do take the time and fill out those surveys and give us the feedback. So thank you. Have a great SDC. Thank you for joining us today, and look forward to hearing more from you and seeing how else we can deliver value. SNIA is your organization. We're here mutually benefit for the members. Let us know how we can make your lives easier and for SNIA to be more valuable in the future and today as well for your companies, your strategies, and what do you do in the industry. Thank you.
Good morning, everyone. How are you? Good. Good to see so many SNIA members here and prospective members, which are important to me. I'm Marty Fulton. I'm SNIA's Business Development Representative, and it's wonderful to have all your faces here. Great crowd yesterday. We even had 75 people for the BOFs from 7 to 8. It's fantastic. So I have the pleasure this morning of introducing our keynote speakers. And the keynote speakers are here due to the great work of this SDC agenda team made up of the Technical Council and other senior members of SNIA's volunteer organization. So I'd like to give them a big round of applause for all the great work they've done. So our first speaker is Andy Walker, Vice President of Product for Spin Transfer. Andy focuses on turning STT's leading edge technology into marketable products. Spin Transfer is a SNIA member, very pleased about that. Before joining STT, Andy was founder and CEO of Skilltron, where he developed new approaches to ultra-high endurance 3D flash memory. Andy holds over 40 US patents and is the author or co-author of over 30 academic articles. He's also given presentations at many technical conferences, including SNIA's Persistent Memory Summit. Andy is a recognized industry expert in 3D flash memory, thin film transistor physics, and solid-state memory technologies in general, and earned a PhD from the Technical University of Eindhoven. Welcome, Andy.
Thank you very much. It is a great honor to be here. I gave a similar, can everybody hear me? Can everybody understand my accent? So I gave a similar talk at the Flash Memory Summit a few weeks ago to a small but enthusiastic crowd. And I'm pleased to see there's more people here, but maybe the size times the enthusiasm might be the same. But let's hope that I can instill the same kind of enthusiasm in this subject that I have for it. I've been boring my family for many years on this topic, so you are now my next victims on it. It's a very interesting area. As an engineer, scientist type, I always like going down to the fundamentals. What is it that this whole industry is based on? And this is one of the key parts of it, tunneling. I only have one slide on quantum mechanical tunneling, and it's a pictorial slide. But I want to stress from that slide what the result is. What result do we use when it comes to flash memory? And also spin transfer tech, STT-MRAM as well. So the concept of tunneling came about in the late 1920s, and it was the first successful application of the new quantum mechanics at the time. And I'll go into that as well. But before I do that, I want to give you a small anecdote. Where I come from, if we go for a walk in the mountains, we get to the top of the mountain, we usually find a pile of stones, and it's called a cairn. And then we take a stone ourselves and we place that stone on top of that mound of stones. And it's basically in honor to those who have gone before. So this industry is based on thousands and thousands of people working, being innovative, using creative ways of building products based on fundamental technologies. So this is one of them, and I hope to show you with this golden thread of tunneling how it all fits together for our industry. Okay? So let me go to the next one. So what is the link between, for example, alpha particle decay, 3D NAND, and STT-MRAM? It's basically tunneling. So if you look, I think this is the one, yeah. If you look here, this is a paper that came out in Nature in 1928, Gurney and Condon, and it was the first successful application of the new quantum mechanics at the time to explain alpha particle decay. So it's basically the alpha particle stuck in a nucleus and the ability to tunnel out of that nucleus and be measured outside the nucleus. It solved many, many problems, many unusual problems. And then if you look here, I have to quote this actually. Much has been written of the explosive violence with which the alpha particle is hurled from its place in the nucleus. But from the process pictured above, one would rather say that the alpha particle slips away almost unnoticed. So it tunnels its way through that barrier. Then you look at 3D NAND. So these are pictures of, or a diagram that I drew in, but the actual cross-section of a device. And you can see here, it's basically a field effect transistor. And you've got the channel, you've got this funny-looking dielectric stack, and you've got the gate. Here is the tunnel dielectric. This is where the electrons tunnel through into a charged reservoir and out of the charged reservoir. So I'll go into more of that, the evolution of that structure. And then STT-MRAM looks a bit complicated. We've got these magnetic materials, but we've got a tunnel barrier, a very, very thin layer of magnesium oxide. And again, it's all about electrons tunneling through that thin barrier and doing their stuff. We'll go into that as well. But at the foundation of the whole thing is this tunnel mechanism. So I want to tell you, at the Flash Memory Summit, I was walking around some of the booths, and one of the booths was from one of the major manufacturers of NAND flash. And one of the engineers there told me that they have invented 3D NAND with charge trap as the mechanism to hold the charge, right? And there's a big battle going on between, as you know it, some on one side using charge trap and some on the other side using floating gate to store charge. Now, I had to tell him that this actually goes back, this storm in a teacup goes back to the 1960s. And I'll show you where that came from. But floating gate versus charge trap in a non-volatile memory goes all the way back to 1967. And I'll show you. Okay, so that's the lead in. So this is what I'm going to talk about. What is tunneling? So that one slide. Then tunneling in solid state memories. Why it's important, where it arises. Damage. By tunneling, we create damage. So for example, we create endurance limitations in NAND flash. That's the damage from the tunneling mechanism. The golden thread of tunneling. So this is then a few slides on the history. What happened when? Who did what? So this was quite interesting. This is me going into the Computer History Museum archives and looking at the original Fairchild lab notebooks and finding the original experiments done on tunneling in silicon devices. And from those scribbles, it's amazing that this whole industry took off, right? And then also a bit about STT-MRAM. It uses a tunneling mechanism, but it's an unusual one. And there's a conundrum associated with it. I'll show you. Tunneling engineering, there's certain things we can do in design, circuit design, but also in the architecture of a device to improve the endurance, to reduce the damage of tunneling. Some conclusions, and then tunneling in Silicon Valley. I'll show you some of those lab notebooks or extracts from, and then acknowledgments. Okay, what is that? This is the single slide. The single slide on the quantum mechanics of tunneling. So remember, the whole thing is this Schrodinger's equation, and you've got this wave function and so on. And it turns out the amplitude of the wave function is the square root, basically, of the probability of finding the particle at any place in time, any place in space. So you can see here, for example, this would be a barrier. Here's a barrier. On this side of the barrier, classically forbidden to a particle, right? On this side of the barrier, it would be constrained within that region. And then we have you can imagine a bucket. So we put all these marbles into a bucket, and then we leave them overnight. And then the next morning, we find that one of the marbles has got out. So not knowing quantum mechanics, you'd think, oh, somebody must have taken it out and placed it outside. But in quantum mechanics, if the particle is small enough and so on, then there is a probability. The probability is given by this function, the square of that, of the amplitude of the wave function. There's a probability of finding it outside in the forbidden region. So what would happen if we had a barrier here? And then here's the total energy of the particle. And then this is the potential energy diagram of what the particle has to endure. So you can see here, if the width of that barrier is sufficiently small, there's a probability that it will find itself on the other side. So that's it. So this book actually here, 1940 book, Elementary Quantum Mechanics by Greiner, the same guy that did the alpha particle decay, is one that I got for free about 30 years ago at Philips. They were giving out these books, trying to make more space in the library for other books, and I wrote my name in a list for this one, and I got it. So I had it for many, many years, and then finally I decided to plod my way through it. And then it paid off. I started understanding it again. So this is, and it's pictorial. It's a way of understanding something pictorially, which is very powerful, for me anyway. And he writes here, we shall not expect to find in quantum mechanics anything so definite as the sharp dividing surface. So that's the key. So for electrons, they can tunnel through barriers. And that's the foundation of NAND flash. So tunneling in solid-state memories. 2D NAND, charge tunneling to and from a floating gate. There were some who tried to use charge trap in the 2000s, but they had problems. But so most, all 2D NAND products are floating gate based. That's the reservoir where the charge is stored. 3D NAND, charge tunneling to and from silicon nitride or floating gate. So there was a resurgence of silicon nitride as being the reservoir for storing that charge. There's also classic Sonos, charge tunneling to and from a silicon nitride. Sonos goes all the way back to the 1960s. And then STT-MRAM, and I'll talk more about that. Tunneling between magnetic metals. But for these, for flash, for 2D NAND, 3D NAND, and classic Sonos, the basic components, there are three basic components. When you boil it all down, You need a field effect device. You need a transistor, some kind of device that can be used as the electrometer for measuring the absence or presence of that stored charge. So that's the field effect device. Then you need the charge reservoir. You need to store it somewhere between the gate and the channel of the transistor. That's the reservoir, nitride or floating gate, silicon nitride or floating gate. And then you need a mechanism to move the charge in and out of that reservoir. That's the tunnel mechanism. Those are, in all cases here except for STT-MRAM, those are the basic components of what we're dealing with. And then all the innovation comes around how to build architectures based on those three components. How do you build the field effect device? How do you build the charge reservoir? What's the optimized version of that, and so on? And then the tunnel mechanism. How do you optimize the tunnel mechanism so we get maximum endurance? And it goes all the way to total cost of ownership of an SSD. If it only has a certain number of times you can fill and empty the total memory, and you have to throw it away and spend more money to have another one, that's where that endurance comes in. How to engineer the tunnel mechanism to maximize endurance. So those three things, remember those, because once we start talking about these various types of memory, you can see the three mechanisms at work. For example, here's 2D NAND. This is some cross sections I got from Dick James when he was at Chipworks and then at Tech Insights. When you see something like these cross sections, you see the engineering that has gone into this. So this was 128 gigabit, 16 nanometer 2D NAND from Intel Micron. So you see here's the string. Here's the string in the 2D NAND. And here's the last 2 bits. And you can see here the control gate, the floating gate, the tunnel oxide, and the dielectrics between the gates. So we've got the MOS. We've got the field effect device. Here's our field effect device. Here's the channel. Then we've got the main gate, and then we've got the stuff between the main gate and the channel. Here's the reservoir for storing the charge, and here's the tunnel oxide using the mechanism for that program and erase through tunneling of the electrons to and from the floating gate. And this sort of, over many, many years, sort of distilled out to be about 7 nanometers to optimize the endurance. Okay, so that's the 2D NAND. And as we all know, that is having problems in scaling below half pitch of about 15 nanometers. So then the manufacturers saw this coming, so they started working on the 3D versions. But again, 3D versions have the same 3 mechanisms, structures involved, the foundations. Here's 3D NAND. Looks complicated, but again, here's some beautiful work from Chipworks, Tech Insights, cross sections. You can see the strings going up and down. Here's it turns out to be the contact to the source at the other side. It's an amazing technology when you look at it. When this first came out in 2000, first one in 2007, I said, the expert, this will never work, right? So what I say now is it will eventually not work, right? Because they'll hit a sufficiently tall structure that they can't do it anymore. But so look here. So the cross sections here looks complicated, but it's very straightforward if you look at it. Here's the MOS again. So we've got the field effect device. The field effect device, here's the gate, this metal, this tungsten metal here with tinitride. Then we've got this dielectric of the field effect device, which is includes the reservoir for charge storage, the silicon nitride. Then we have a tunnel dielectric, and it's a complicated looking thing with silicon oxide and silicon nitride, right, to optimize endurance. So a lot of engineering has gone into that stack of dielectrics to optimize endurance and retention. And then we have the channel. So we have the field effect device, we have the reservoir for storing charge, and we have that tunnel tunnel structure to get the charge in and out of the reservoir. That's all it is. The rest is the engineering of putting that together in a way that leads to reduced cost per bit. But that's basically what it is. So the tunnel mechanism right here. You can imagine alpha particle decay right here. Then I did some work in the 2000s, in the late 2000s, trying to build a device. So I built a device that could boost endurance, for example. So I built a thin film transistor. This is a cross-section of the thin film transistor, which has two gates. It has a polysilicon gate on one side, then the channel here. You can imagine the channel coming out of the page, and then you've got another gate on the other side. And the key thing is here. Here is the field effect device again. One device here, another device here. This one optimized for charge storage. This one optimized for passing a current independent of that charge storage. So what this did was it allowed you to optimize the ONO, the tunnel oxide and the nitride and the blocking oxide independently of disturbs, past disturbs, which turns out to be important because then you can boost the endurance by orders of magnitude. So this is something I worked on about 10 years ago. But again, the field effect device, the reservoir, and the tunnel mechanism. Okay, so the three things are still there. Again, put in a different way, an architecturally different way. Then we come to this unusual beast, STT-MRAM. So I joined this company about a year ago, and the background to this was they had come up with a piece of IP, a design piece. This is not a plug. This is supposed to be the reason I joined, right? I can explain it like this. They had come up with a piece of designed IP that would fit with anybody else's process that would boost the endurance by orders of magnitude. So this was the claim. So then when I saw how the thing would operate, then I started to understand this stuff too, at a sort of fairly fundamental level, not at a complex level. But this was a piece of design IP that could boost the endurance by orders of magnitude in a non-volatile memory. This is highly unusual. I'd never seen this before, because usually to boost endurance and balance retention, you go into the fab, you change materials, you change structure, and you get maybe half an order of magnitude improvement. This was highly unusual. And then we got silicon, and then it showed itself to be true. So this is quite exciting too. I'll talk more about this. But anyway, the structure here is magnetic materials, magnetic metals, separated by a thin tunnel oxide, and then with the magnetization vector of this top layer being switchable, the bottom layer being a reference kind of material. And it turns out the electrons, when they tunnel, the resistance of this stack depends on the relative directions of these magnetization vectors. So this is a low resistance state, and this is a high resistance state. So the electrons find it easier to tunnel through when both of these are aligned. Now, for switching, it turns out you need quite a high current to switch that. You get this filtering of the spins of the electrons tunneling through. If you get enough of them, they will flip this magnetization vector. So you can flip between a high resistance to a low resistance state. But the problem is, I'll tell you more about that, it's unique in solid state memory. It's a stochastic process. Sometimes with the same bit, with the same current, the same voltage, is a probability it may not switch. And that's the fundamental difference between this and all other solid state memory. So I'll talk about that too. And how it relates to tunneling and tunneling damage and so on. Is everybody following this? Getting enthusiastic about the If there's anything to take away from this, is those three things, right? If you're a systems engineer and you boil it down to the fundamental foundation, it's the three mechanisms: the field effect device, the reservoir for charge storage, and the tunnel mechanism. And each of those had to be invented along the way, right? So we'll go into that in a minute. Who invented it? When was it invented, right? They had to be in place before the next step could be taken, right? Okay, so there's also tunneling damage. So when we tunnel through a barrier, it creates damage. And the rule of thumb is tunneling creates more damage in thicker tunnel dielectrics. And what is thick and what is thin? So thick and thin, about 3.5 nanometers is regarded as thick in the 2D NAND and 3D NAND. And less than that is thin for classic Sonos and STT-MRAM. Because if you look at STT-MRAM by itself, if you take care of the stochastic nature, you can get to about 1 million to 100 million cycles. If you look at 2D and 3D NAND, depending on the SLC, MLC, TL, whatever, you can get anywhere between a few thousand to maybe 100,000 cycles, right? Classic Sonos, much thinner dielectrics, you can get up to 1 million cycles or more. So what is the damage and what are the consequences? So charge trapping is one of them. These electrons are tunneling through, back and forth across a thin oxide. They get trapped. What does that do? That changes the threshold voltage of that field effect device. It's no longer the fresh device that came out of the fab. It's got electrons stuck in the oxide or stuck somewhere in an interface trap that changes the threshold voltage of the device, and you can't get rid of it. So what it does is, if you look at the population of threshold voltages within a population of bits, they start sort of widening, and then it gets more difficult to tell them apart. A 0 and a 1. And you also get shifts in the current voltage characteristics. It might be more difficult to have current flow through a device that's supposed to be off. And then it gets, again, more difficult to sense the state of the device. So charge trapping is one. Stress-induced damage. You get things, damage induced in the oxide, breaking of bonds that result in more trapping and so on. So you get this sort of what they call stress-induced leakage current. You get these traps in the oxide and charge can hop out. They're supposed to be stored in the oxide. And you get wear out and breakdown. If you take it too far, the thing just breaks down. You get a short between one of the floating gate or whatever and the substrate. So those are things that over the years, I'll show you the history, over the years have been engineered around. So this is again, the interesting thing. We come as a group of innovators up against the problem, and we find solutions which are not usually in your particular area of expertise, but require others to come in from other parts of the industry to fix. And of course, as an engineer, you think, no, my expertise will fix this. But then what you find is, and I think this industry shows it, what you find is the fixing of these problems requires cross-functionality, and that brings people together. So there's a social aspect to all of this as well, bringing people together to solve problems, right? And these problems become stressful because there's a momentum in this industry to make things work. And it becomes, the time to a fix becomes very short. So you need to be on the ball all the time. But it's cross-functionality, that's the key. So, the golden thread of tunneling. So some of these things you probably won't be able to read, but SW gave me a good piece of advice. In the final document, I will include these blown up versions in an appendix. So if anybody is interested, they can go after it themselves. They can bore their families about did you know that Kang and Atullah came up with the first silicon-based transistor? All this kind of stuff, right? So you can see eyes glazing over at the dinner table, but you know. So I will blow up these, put them in an appendix, and you can do your own research. It's really, really interesting area. So anyway, so we have, it's a golden thread. So tunneling is the golden thread that connects all of this together. So from fundamental physics to technological innovation. So look, here's the fundamental physics. So here's that diagram, this sort of leaky barrier, getting across a leaky barrier. Then one of the first applications, so we had the alpha particle decay, but then Fowler and Nordheim came up with the use of tunneling to explain how electrons would get out of a metal in a very, very high electric field. So that was called Fowler-Nordheim tunneling. So Fowler is interesting because he was the son-in-law of Lord Rutherford. And he was at the same institute in Cambridge, and they were sort of working together. And Nordheim was a postdoc, I think, and he worked with von Neumann. So von Neumann was, he and von Neumann came up with one particular aspect of quantum mechanics, the operator formalism. So these people got around. But this turned out to be of fundamental importance to the tunnel mechanism that was used in silicon devices. FN tunneling, they call it. So many people will drop the names, FN tunneling, Fowler-Nordheim tunneling. But the people who were involved, it was back in the 1920s, working on a different problem. But the physics then was used in the 1960s, okay? Then a lot of things happened, but then the MOSFET, the field effect device, the silicon-based field effect device, there were rumblings about field effect behavior from the late 1920s, actually. Lilienfeld, an immigrant from Lvov in what is now Ukraine. But that, and then Shockley tried to patent the field effect, but he couldn't patent it because Lilienfeld had already patented it, the main concept. Then it was Kahn and Artulla who came up with the first silicon-based field effect transistor. And then things took off. Then you had, it was a small step, Kahn and Simon C, working on Fowler-Nordheim effects in a silicon-based device that could use the Fowler-Nordheim effect to store charge in a reservoir, a floating gate, if you like. So that was floating gate in 1967. But Charles Trapp was also 1967 to 1968. We had Wegener on a variable threshold transistor using nitride as a storage mechanism. So you can see all the, this goes all the way back to the 1960s, right? Then you had a Monos memory element, basically a Sonos device. So you had a gate, metal gate in that case, oxide, nitride oxide, silicon. And they found, we could change the threshold voltage of that device by storing charge, tunneling charge into and out of that nitride. And then Lenzlinger, remember that name, because I'll come back to that. Lenzlinger and Snow, describing the mechanism of Fowler-Nordheim for what Simon C. and Kang had been doing. This is at Fairchild. And then Lenzlinger also did a lot of work on the foundations of that, and I'll show you, that's the guy, Martin Lenzlinger. That's the guy whose lab notebook I was presented with by a lady with white gloves at the archives of the Computer History Museum. And it was quite an emotional moment when you think how far it's come, right? Then you see Froman-Benchowski and Lenzlinger again in Fairchild. Knowing the history, it's quite interesting to see, Benchowski eventually went to Intel. I think Lenzlinger stayed at Fairchild. And here's Harari, Eli Harari, with the first E-squared PROM that used tunneling for in and out of the floating gate. Big device, single device, big device. And Eli Harari had done a lot of work in the 1970s on his PhD, postdoc actually, PhD in Princeton on electron tunneling in thin oxides. So he knew what the damage was in that mechanism. And then in the late 80s, I'll show you, he came up with, oh, how can we mitigate against that damage using design and system techniques, the controller. Then Masuoka, Toshiba, flash, first flash device, 1984. Then you can see where it's going, right? So NAND flash, 1988. The 1988 is the first NAND flash that used tunneling for both program and erase. They tried the year before to use a hot electron injection mechanism, but it never got anywhere. So this was really the first NAND flash. This one is the mother of all that came after it, okay? And then multi-bit. So Harari, Eli Harari and team working on, let's store packets or subpopulations of electrons in the floating gate so that we can tell we have one population versus another population, so we get multi-bit within the field effect device. And then system flash, how to control, how to take charge of, how to count how many times a cell has been written and erased, knowing that it will wear out eventually. So that control and monitoring of behavior and shifting data around within the flash is basically the controller, the system created. And basically, so NAND flash plus those concepts led to the industry that we have here. And then limits of 2D NAND. In about 2016, there's, it's coming to an end after all the engineering. So then a lot of work was being done, knowing that the 2D NAND was going to eventually have problems. A lot of work was done then on thin film based devices. Thin film because you can stack them on top of the substrate, one on top of the other, a 3D architecture. And a thin film transistor is nothing special. It's just the field effect device, but with a thin layer instead of the whole bulk substrate as the channel, if you like. So then I had the good fortune of being involved in matrix semiconductor from about 2000 to 2004. And we created the world's first 3D TFT Sonos memory cell. This was in the VLSI Symposium in 2003. And this was, I remember taking that wafer out to the fab, sticking it under in the measurement facility and seeing the current voltage curves, right? And then that was the start of boring my family to death about how beautiful these curves were and how this was going to take over the industry and everything. So it was an amazing thing. But anyway, you see a field effect, an unusual field effect device with ONO, charge trapping, and the ability to stack. So that was 3D. Then we went Macronics. Macronics published the first TFT Sonos NAND string, right? And they showed the behavior there. And then I started a company to build a dual gate. I spoke about it before, thin film transistor Sonos device that could boost the endurance by orders of magnitude and still be non-volatile. So this was the rise of monolithic 3D flash, but that's not the type that eventually took off. But elements are there, the thin film transistor nature and the storage in a reservoir and the field effect device. So then came bit cost scalable, the BICS architecture from Toshiba. Toshiba were always seemed to be the ones breaking new ground when it came to the architecture and what eventually became a manufacturable process. So here, bit cost scalable. This was 2007. The first attempt at making this structure, which is basically the mother of all 3D NAND now. Now, not far behind was Samsung. Samsung came up with their version. They called it terabit cell array transistor, which is now VNAND or whatever, but similar kind of structure, but different process flow, maybe more manufacturable and better for lower resistance paths and so on. And I think this one eventually is winning out. I'm not sure about the actual differences anymore in manufacturing, But this was the rise of vertical channel 3D NAND. So 2007, 2009, Toshiba, Samsung. And there it is. So this was, again, Chipworks, Tech Insights. Dick James sent me these. And you can see the structure here. But again, look how complicated it looks. But it's not. It's the field effect device in a ring. But here's the gate. Here's the reservoir of charge storage. Here's the channel. Here's the field effect device. Here's the tunnel dielectrics, and so on.
Andy,
Yeah.
Something that is really impressive about that picture that I think you should mention is that those little dots are individual molecules or atoms.
Yeah, here, silicon atoms here. Isn't that beautiful? And the other thing that's interesting about, thanks, Jim. The other thing that's interesting about this is all other NAND, all other flash and so on, was built in the substrate. So the substrate is monocrystalline silicon. This was then polycrystalline. This is polycrystalline silicon. And when you go from one to the other, you limit the mobility of the electrons in that material. So the amount of current out of this is much lower than in the substrate, if you build it in the monocrystalline substrate. So one of the battles the challenges that the 3D NAND folks have to deal with is to increase capacities, they have to lengthen the string. So the string is one big long resistor. So you can imagine a big long resistor combined with much lower mobilities of the electrons in that resistor lead to much lower currents. So they have to deal with sensing that current. Okay? But yeah, an amazing structure. Now, a few words on STT-MRAM. STT-MRAM is has a stochastic nature about it. It looks complicated, but if I take a bit and I program and erase it with the same voltage each time, now and again it won't program and it won't erase. That there has a probability associated with it. That probability is given by this stochastic top hat. This is the right error rate. So the probability that it will not switch as a function of the voltage across it, positive and negative. Very low voltages, probability that it won't switch is high. It won't switch. To make sure that it switches, you have to apply a relatively high voltage, a relatively high tunnel current. So at the product level, you need to hit it hard. You need to apply a long pulse or many pulses or whatever. So what that does is, a single cell, you may miss that it doesn't switch. But at a product level, you have to hit it harder to make sure that the population has a low right error rate. So what that means is that you limit the endurance because the tunnel current is high. So that's the limitation in STT-MRAM. And what the company spin transfer has is a design technique that can mitigate against that. So I won't go into too much detail in that, but that's what attracted me to that. It was an engineering of the tunnel mechanism. So so tunneling engineering, right? This is a very interesting area, right? NAND flash increases electrical bits per cell. They want to increase the capacity, increase the density of the material. But what they do is for SLC, MLC, TLC, and QLC, the endurance goes down because you've got less space, electrical space between the populations of threshold voltages within that field effect device. And they can't go too thin with the tunnel oxide because of disturbed mechanisms. So they will be limited at about, per cell, about 100,000 cycles. That led me to this kind of structure here, which can get to millions of endurance cycles. So you engineer it, given the constraints of the the field effect, the reservoir, and the tunnel mechanism, you can engineer around that and boost the endurance with an architectural change. And then STT-MRAM endurance boosted by design techniques. I won't go into that if anybody's interested. But basically 6 orders of magnitude gain, allowing for a potential for SRAM and DRAM replacement if it can be made manufacturable. But it's all tunneling engineering. So conclusions a long and illustrious history, the foundation of many, many solid-state memory technologies. It creates damage and must be monitored. And you can engineer around those. And so that engineering and cross-functionality, design can deal with it. In NAND flash, design and the control of the system deals with it, right? Hides that damage, right? Up to a point. Architectural structures of how you put the elements together in the process, that can boost the endurance as well. Continues to grow in importance. 3D NAND evolution, other 3D NAND solid-state memory approaches, and STT-MRAM. Okay, so this tunneling in Silicon Valley. This was Fairchild 1967-68. This was from Martin Lenzlinger's notebook, November the 1st, 1967. This is a Fowler-Nordheim plot of tunneling through a thin oxide out of time. Okay, so this is his lab notebook. Here he says, conclusion: the current through the oxide is limited by, the current through the oxide is limited by the tunnel injection. And this was a memo he wrote to some, turned out to be quite famous guys in the end, Andy Grove, Gordon Moore, and some other ones you might remember here. This is January 25th, 1968, just a few months before they went off, and some of those went off and started Intel. I wonder what was going through their minds at that time. Was it tunnel mechanisms, or was it this new company that they were developing? Okay, acknowledgments. Eli Harari, I've spoken to him on many occasions. Very interesting insights into the history of the whole thing. Dick James, I've mentioned. Malcolm Longare, University of Cambridge, to make sure that what I present here on the quantum mechanical front is not complete nonsense. Thomas Boone from Spin Transfer Technologies for that cross-section I showed you. The Shustek Center in Fremont from the Computer History Museum, and the Cambridge University Press for allowing me to show those diagrams from that book. Okay, that's it. Do you want to?
We could take it to the back.
Oh, okay.
So Andy, you'll be here later
Yes.
for any questions?
Yes.
Okay, excellent. Thank you so much. Are you awake? I'm very pleased to introduce our next speaker, Gary Greiner. I've known Gary for a number of years and have had the pleasure of hearing him speak at numerous events. Gary Greiner is the leader of the High Performance Computing Division at Los Alamos National Laboratory. As division leader, Gary is responsible for all aspects of high-performance computing technologies and deployment at Los Alamos, including management of the R&D portfolio. Gary is also the U.S. Department of Energy Data Storage, I/O, and Data Management National Coordinator. In this role, Gary helps manage the U.S. government investments in data management, mass storage, and I/O. Gary has 30 active patents in the data storage area and has been working in HPC and HPC-related storage since 1984. Welcome, Gary.
Hello? Test, test. Thank you very much for the intro. That's been a great week already, and I was at a DOE storage conference last week, and interestingly enough, I heard the words last week, count key data, and this week I heard Christoph last night say the word channel program, and so I feel like I've been on the merry-go-round and I've come back around again. So anyway, let's get started. I've got a fairly long talk, so I want to get it in. What is Los Alamos? I never really know how many young people will be in the crowd that don't really know what Los Alamos is. I think there are probably history books now that have been written that gloss over the whole thing. But Los Alamos is where the nuclear weapons community began and where the nuclear weapon first was developed. In fact, it's interesting, the last speaker talked about John von Neumann, and I actually have a picture of John von Neumann standing right there next to Robert Oppenheimer in front of the machine he built at Los Alamos called Maniac, which was a machine right after ENIAC. And interestingly enough, we ran the first problem on ENIAC, which was the first machine in the US. And my mentor actually was one of the programmers, and she had the box of cables that she used to program that machine in her office, and she was quite a character, a wonderful role model. Anyway, so this is sort of what we do. We tested in Nevada for a number of years. We have a number of non-critical test facilities, a hydro facility, a neutron beam facility, and so forth. And the whole idea is to make the world safer from nuclear weapons and make them safe to use if we had to use them, and safe to roll them around, and so forth. So that's what we do. We've been computing for an awfully long time. As I mentioned, Maniac was roughly the third machine in the US. It was a big tube machine. Had a machine called Stretch, which is interesting. It was the forerunner to what was to become the IBM 360 series. It was considered to be a colossal failure. It was supposed to be 10x faster than Maniac, and it was only 4 times faster than Maniac, and IBM said, God, that was really bad. And then they ended up making their living off of that architecture for the next 30 years. The first Cray 1 came in to Los Alamos and didn't work for 6 months. It worked great in Minnesota. It didn't work at all in Los Alamos. Why? Because we're 7,200 feet in the air, and we have a few more cosmic events than you have at sea level. And so we had to ship the memory back, and they had to add some sort of protection to it, which is interesting. And we still suffer from those problems today. Lots of YMPs and XMPs. The CM2, the CM5 was interesting. For those of you that watched Jurassic Park, you'll recognize that machine. But that was actually the first top 500 machine on the first top 500 list ever, which is kind of interesting. It was, I think, about 1,200 sparks. And then other machines that we've had over the years, including our current machine, Trinity, and we've got a D-Wave quantum annealing machine, which if you're into quantum effects and things like that, which it sounds like our last speaker would love to delve into that, then there's a machine for you. And then we're in the process of buying a new machine called Crossroads to be installed in 2021. So anyway, we've been at this a really, really long time. Some interesting storage projects and products that we've been involved in. DOE or LANL has had a whole lot to do with, either wholly funded or not completely wholly funded. The list is pretty large. But we had a whole lot to do with all these, essentially, and I'll take you through some of that later. The one in the bottom corner is very interesting. It's an IBM Photo Store. There were 4 of those made, one for NSA, one for us, one for Livermore, and one for the Census Bureau. And IBM thought that that was all the storage they would ever build in the world at the time. Those were microfiche, and you burned 1s and 0s on the microfiche in a barcode pattern. And there was a robot the size of this room, roughly, that was full of these little microfiche thingies. And my predecessor that ran the division used to say you could tell when the computing people had a really good night, because you'd come in and the whole place would smell like plastic burning, because they decided that's good data, we want to store that, we want to keep it, and they would essentially burn whole bunches of plastic to get all those data stored. Anyway, hopefully you recognize some of those names on there. So a little bit of background, quick, how we do things at the lab. So we have one big premier machine typically. It's Trinity, and I'll tell you more about it in a minute. It has a local scratch file system, about 100 petabytes, and runs at about a terabyte a second. And then we have a whole bunch of capacity machines. So the big machine, think 10 to 20,000 nodes. The smaller machines, think a few thousand nodes, and there's a whole bunch of them. And we run 2D and 1D jobs on the smaller machines, and we run big 3D jobs on the big machine. There's some site-wide scratch file systems that are available to this environment, so they're not private, they're shared amongst all the supercomputers. We've got a parallel archive. We helped develop HPSS. It's parallel tape, so you stripe data across lots of tape robots. And that's about 10 gigabytes a second, and the data is held forever, literally. We've got an NFS, for home and scratch and things, or home and project and things like that. We have a cluster set aside just for moving data, so you submit a job to the cluster, and it does nothing but move data for you, move a petabyte here, or move 10 petabytes there, or whatever. That's called the file transfer agent cluster, and then we've got some WAN stuff going to Livermore so that we can back each other up and so forth. So that's what our environment looks like, sort of roughly. The thing in the middle is our site-wide InfiniBand, essentially storage area network, and I'll tell you a little bit more about that in a minute. The largest machine is a 20,000 node machine. It's Haswell and K&L, a few million cores, 2 petabytes of DRAM, 4 petabytes of NAND flash that runs at 4 terabytes a second, 100 petabytes of scratch that I talked about before, which is a disk-based parallel file system. And then we have this thing called Campaign Store, and I'll get into why we have that in a minute, but it grows by about 30 petabytes a year, and it runs at about a gigabyte per second per petabyte. And then 60 petabytes of site-wide parallel tape archive, which actually is quite small, and we're not growing the tape very fast, and I'll get into that in a little bit as well. You see a picture of the machine. It's about a quarter of an acre kind of machine, and it's in the 10 to 15 megawatt range, so it's kind of a typical machine in the size. And then you'll notice that the pipes there, that's 36-inch steel water pipes. That's to hook the machine up. So the wires is one thing, but take the heat away is another. So that's the pipes that actually were put into the building to take the heat away from that machine. Unfortunately, those pipes full of water weigh an awful lot, and so I actually had to drill holes in the concrete floor in the basement, erect essentially a bridge and hang the thing, or it would have crushed the concrete. And so it's the really big pipes. Anyway, so and that sort of stuff costs a lot of money, which I don't like paying, but anyway. So I want to take you back a little bit through history, and then later on I'll hopefully point towards the future. This was sort of a battle early on that I was involved in the middle of my career, roughly, circa 1994, 95, on trying to get mass parallelism implemented at the laboratories and in HPC environments. And essentially at the time we basically got together and said, okay, well, we want to build these crazy clusters with thousands of nodes in them. How are we going to do I/O off of them? And we didn't really know. And so we actually had a conference in this time frame, and it was called the Intergalactic Parallel File System Conference by Peter Brahm. And there was a bunch of luminaries there. Garth Gibson was there, and Peter Brahm was there, and Roger Haskins from IBM was there. And essentially, we ended up trying to start multiple projects to get this problem solved. One of them was Panasys, so we essentially got together with their venture capital and partnered up to try to get them started. We helped move IBM from what was then called PIOFS into now is what's called GPFS, but we had a whole lot to do with that, including writing some pretty large checks to make that occur. We actually started some interesting work at City, at University of Michigan, Peter Honeyman's group, to invent what became what is now known as NFS version 4 and PNFS. In fact, we funded the first prototype of that work that was done actually at Sandia Lab. And so that's moved forward. That's interesting work, compound RPCs and all the wonderful things they added there. We wrote a contract to University of California, Santa Cruz and started this thing called Ceph, and I've got an interesting story about that I'll tell you about in a minute. We issued the contract in 2001 to start what is now known as Luster. And I spent 4 years of my life every Thursday morning with Peter Brahm trying to get that thing to work, and it finally did, I guess, sort of. It's used quite a few places. In 2001, we had to invent this thing called a parallel scalable backbone to connect the multiple supercomputers to the multiple parallel file systems, which was an interesting concept at the time. To build a terabyte per second network back in 1995 was tough, and so anyway. And then in 2009, we did this thing called parallel log structured file systems, which I think has changed a lot of thinking in this community, in the HPC storage community, and I'll tell you about that in a minute as well. This is my Ceph humble start story. So we wrote this contract to University of California, Santa Cruz, Darryl Long and that bunch over there, and we told them we wanted them to study scalable metadata in parallel file systems, and we all wanted them to study scalable security. Security has this, in POSIX file systems, has this hierarchical, unscalable thing about it, and we wanted them to study how you could get over both of those things. They came back and said, we want you to pay us to write a user space object-based parallel file system that is prototype, so that then we could go and play around with these ideas that you have about how do you scale metadata and how do you scale security. And we said, okay, fine, take the first 3 years of a 9-year, $300,000 a year contract to do that. And then the last 6 years, we'll study these problems that we really have. And there was this guy there named Sage Wild. He was a graduate student, and we ended up with what's now known as Ceph out of that, and Rados, and a bunch of other things happened. Interestingly enough, they took a run at scalable metadata, and that branch still, I think, exists in Ceph, and I think they're dusting that off now that they're back in the file system business and trying to use it. The other thing we gave up on, it never happened. So it was kind of a mid-level success for us, but it looks like it changed a lot of things for the world, which is great. 2 Hpc Io patterns that persist. So there's lots of HPC patterns that exist today. In fact, some of them that actually do quite a bit of reading. But in our world, we do a lot of simulation, so we do a lot of writing. There's 2 kinds of patterns that dominate. One is every process drops a separate file into the same directory. So think 1 million cores, and they all decide they want to drop a file into the directory, a single directory at the same time. So they all just run up within milliseconds of one another and beat the hell out of the metadata server until it gets all the creates to happen into that directory, and then finally you can start writing data. And it creates millions and millions and millions of files as it runs. Then there's N-to-1, which is all million cores decide they want to write into the same file, so they all open the same file, and they all offset in slightly different patterns, and they write, odd amounts, not necessarily the same amount, completely unstructured and stuff. So that's great on the metadata server and just beats the hell out of the data servers. And so either end of the spectrum is kind of hard to deal with, and we've been dealing with for a number of years, and I think we finally beat it into the ground, and I'll take you through how I think we did that. We also published a document recently, which I think is interesting, associated with an RFP that we were involved in, and that is for Crossroads. And we did this for Trinity as well, the machine before. And it was essentially a set of workflows. How do our applications run? What is the input sizes? What are the output sizes? How long does the data have to persist? And so forth. And that's interesting because the persistence, we needed a taxonomy to deal with this and to tell vendors, here's what we're trying to do with your machine for the first 5 years of its life while it's at Los Alamos. And so this is what we want to do with it. Can you help us build a machine that will work well in this environment? So this document is interesting, and it's published, and you can go find it on the web. The parallel file systems, again, I talked about being able to connect them to the different supercomputers that we had. And so this was a long time ago. Back in 2011, we had a terabyte per second network that connected them together. And essentially, it was taking a whole bunch of metropolitan area network switches and connecting them together into interesting ways to try to get, load balanced and failover to work at the scale. Today, things are much, much larger. Think about 10 terabyte per second networks to connect machines together, which is a lot of wires and a lot of switches and a lot of things to go wrong. But we do this sort of on a daily basis. Well, enough with the history. Let's talk a little bit about some economics. So in 2009, so we were, during the late 90s and early 2000s, we were running along fine. We had Lustre working. We had disks we were buying. We'd buy enough disks to get the bandwidth we needed, enough disks to get the capacity we needed, and everything was wonderful. And then I started running economic models. And I'm particularly proud of this one. The story I tell about this is it's the first economic model I ever did where $1 million was on a log scale, which I thought was pretty cool. Because I couldn't think of any other way to show it. So this is essentially me predicting what size machines we're going to have, how big their memories are going to be over the years, and how many disks and sort of media we were going to have to buy to keep up with the bandwidth and the capacity concerns. And it looked like basically what was happening. We were, a long time ago in the 90s, we were buying enough capacity and getting the bandwidth for free. And as we moved forward, we ended up buying disk drives for bandwidth and getting the capacity for free. And of course, disk drives aren't priced for bandwidth; they're priced for capacity. So it looked pretty horrible from a millions of dollars point of view. So we, did the thing that all good storage people do, and we said, let's throw tiers at it. That's what storage people do, is use tiers. And so we said, there's this thing coming along called Flash. Let's inject that Flash layer and see if that helps. And sure enough, it does help. The blue line there is the bottom line, which is a hybrid system where Flash you use for bursts and disks you use for capacity. And you notice that there's a crossover point back in 2012. It actually didn't happen until about 2014, but it did happen. And so anyway, we came up with the idea that we were going to have to inject a layer. We called it burst buffer, and we kind of wish we hadn't, but we did. And we did the same economic model for the tier below it, which was this parallel tape tier, and below our parallel file system. And always before, we were modeling our archives, and it was essentially archives equal the cost of the media. And that turned out to not be true. There were 2 years that kind of popped out as the new tape drives ended up costing more than the media, and we started asking ourselves, well, why is that? Well, that turns out to be when we were going to buy big machines that had way, way more memory than the last machines we had. And so the sizes of data sets that we had to store on tape were going up and up and up. And so now we're talking pushing a petabyte, and that's a big data set to store tape, even lots of tape drives in parallel. And so the bandwidth started getting us in the tape arena as well as the disk arena. And so we ended up saying, well, gosh, we're storage people. I know what we'll do. We'll inject another tier of storage in here. We'll call it cheap disk storage, and we'll use that for putting our really, really big things on where we need more bandwidth than we can get from tape. And that's what we did. We call that campaign store, and I'll take you through some of that in a minute. The burst buffer hoopla parade. So I walk into the supercomputing and in 2014. It's like, I don't know how many, I've been to 25 of them already. And I walk in and, they're setting up all the booths and everything. And all the storage vendors had this big sign, burst buffers, get them here, right? And I just looked at my shoes and went, oh my goodness, I named it the wrong thing. But anyway, 2 products, 3 really, but two products exist today. DDN's Infinite Memory Engine, which is essentially a tiering solution, and Cray's Data Warp. We use Cray Data Warp at Los Alamos. They also use it at NERSC. They have had really good success at NERSC, and we've had good success at Los Alamos using Cray's Data Warp engine. And essentially, it's just a tier of flash storage that sits in between memory and disk. And we use it primarily for bursting of checkpoint restart data. NERSC uses it for all kinds of cool things. So let's talk about all these tiers. They're not necessarily great for the user, but they're sort of economically a reality. And back before Trinity, we had 3 tiers. We had memory, a parallel file system, and an archive. Now, after Trinity, we sort of have 5 tiers: memory, burst buffer, parallel file system, campaign store, and archive. I put up there sort of the residency times and the sizes for the current machine and the speeds for the current machine. It's sort of roughly about an order of magnitude difference in the bandwidths between the tiers. And you can see that the tiers that we added were those 2. And I've made this prediction. This was sort of an eye-opening slide for a bunch of people a couple of years ago at supercomputing. I was giving a talk at the Seagate event, and I made the bold assertion that parallel file systems will hopefully leave the Earth at some point. And I don't know if that's really true, but what I meant was Flash is getting cheaper faster than disk is getting cheaper on a per byte basis. And at some point, we'll be able to afford a far more Flash and for what we do. And disk is going after capacity. That's its only play that it has left. And so it's going to get harder and harder to write to, look at the various kinds of disks that are out there today. They're getting harder to write to, but they're okay, relatively easy to read from. And that's just going to get worse probably with patterns and other kinds of things. And so It looks very much like disk is going to be the solution for capacity, and flash is going to be the solution for anything but capacity, bandwidth, and or IOPS. And so it's likely that it will sort of press out that high performance disk tier that's in the middle there, and there'll just be low performance disk and flash, and that's all there will be. And in fact, our RFP for the next machine in 2021 more or less says this. So instead of having 3 tiers, having flash, parallel file system, and slow disk, we'll just have flash and slow disk. And of course, we'll have more flash. So think more like 10 or 20 petabytes instead of 4 petabytes, and faster, obviously. So anyway, that's a prediction. I don't know if it'll come true, but it looks like, at least for us, it will by 2021. So this tier here, this campaign tier, this capacity tier, how are we going to provide that tier for us? And so we, from a software point of view, it's cheap disk. How are we going to use it? And you might say, well, shoot, cheap disk, that's easy. Just go buy an object server. Well, we tried that, and it's wonderful for a while. But we have this problem that we wanted low cost hardware. B, we wanted object or some kind of massive scaling. The problem is, A, it's got a really simple-minded API, get, put, and delete. When you're trying to put petabyte-sized files, where you really need at least get stream and put stream and a few things like that. It's really hard to do otherwise. And we've got apps that we've spent trillions, literally, of dollars on that expect POSIX and files and actual folders and not just fake folders and things like that. And so there's people out there, there's lots of trillions of dollars worth of applications that still need some folders and things like that, some POSIXisms, not the whole thing, but at least some. We couldn't really find a decent solution that would solve both problems, that would give us enough POSIXism and enough object-oriented scalable parallelism. And so we looked. In fact, I have this whole slide of all the things we tried and looked at. It could have been Ceph perhaps, but at the time, Ceph was trying to become the best server of virtual machine boot disks, which is great use of it, but at the time it wasn't really solving the problem. We looked at Gluster, we looked at all kinds of things, and a lot of these things that put file systems on top of objects are pretty anemic. I mean, they'll take flattened namespaces and try to make a hierarchy out of them in odd ways and things like that, and it just sort of works. And so we decided we're going to have to write our own, unfortunately, and so we did. It's called MARFS. There's a talk later in the week about it, so if you're interested in massively scalable POSIX on top of object, I'd recommend you go. Anyway, it's trying to be the best of both worlds, use objects, but use scalable POSIX file system sort of semantics for the metadata. I'm not going to go into it again because there's a talk about it. Here's some of the requirements that went into it. So we're basically talking a few hundred gigabytes a second to a few terabytes a second. Billions of files in the same directory, trillions of files total. This, of course, was 3 or 4 years ago. These numbers have gone up. Near POSIX, not total POSIX. And we tried several things again. And anyway, the idea was let's build something small, highly leveraged, and open source it and see what happens. We've been using it in production for a couple of years, and we like it. And you're welcome to get involved if you want. But what it isn't, it's not complete POSIX. So you can't do, like, for example, update in place, or you can't do various things like that. So we shortcutted a few things to make it easy. It is small and lightweight and very leveraged. You might ask, okay, how do you move data to and from these big machines and big parallel file systems? Well, a long time ago, I actually wrote the first one of these, and it's been rewritten like 7 times, I think. Is a tool called PF tool. It's interesting in that it has parallel read or parallel stat and parallel copy, rsync, and compare. And so you basically just point it at a tree and say, here's a trillion files and a few petabytes, move it over there. It's restartable, so you can just keep restarting it until it finishes. It'll even restart if it's moving a single petabyte size file because it knows what chunks it's sent and it will restart, which is kind of cool. So It's pretty neat. It's completely load balanced, so it'll just use what you know, whoever's the fastest. It's completely asynchronous, so it may write a file backwards if it has to get the data moved. And so it's interesting, and it's also open source, and feel free to come get it. How does this campaign thing fit in our environment? Well, it plugs into our terabyte per second storage area network, and it's available for people to use. People essentially use it through these file transfer agents that I talked about. Okay, so we're running this thing along for a while, and we got a whole crap load of disks. And what happens to us? Well, so an interesting story. We're sitting in a pretty room with a big window that's looking out over this billion-dollar machine room with all this crap, all these fans and lights and stuff blinking. And we're having a meeting with Seagate, of all people, and we have this interesting brownout, and we lose 441 disks in the same day. And 441 disks in the same day for the population isn't really huge, but it's still quite a few disks to lose. And so we started talking about how we're going to solve this, and we started modeling it, and actually John Bent at DDN helped us model some of this. And we were using erasure and a single tier of erasure, and we decided we're going to have to go to 2 tiers of erasure. And you can see the difference at the bottom. Those 2 bottom curves on number of simultaneous failures are, and for different scenarios, 22 plus 8 and 44 plus 16 and 170 plus 70, which actually is pretty good, but that's crazy to calculate. And then we did this 2-tier, which is 10 plus 2 on top of 17 plus 3, which turns out to be what we use now, and we really, really like it. And there's a talk about it, and so I'm not going to go into it any further. This is kind of what it looks like. It's a tier of erasure in parallel on top of a whole bunch of ZFSs. So the whole thing looks like just a crap load of ZFSs, 17 plus 3s, just a bunch of them. And then this thing does 10 plus 2 on top of it, and it's really pretty fast and pretty cool. And it's open source, so come get it. We thought about, well, gosh, if we wanted to use tape, what are we going to do with tape? And we're seeing this phenomenon with tape, that expensive tape is kind of disappearing, and cheap tape is kind of all that's going to be left at some point, and so you're going to have to erasure across it to be able to use it. And so we think we've got a built-in solution for how to do erasure. Just plug in different tape systems down below, and just like we did ZFSs, and we instantly have a fairly inexpensive way to do erasure across tape. Let's talk a little bit about the future. Run through this really fast. So we think we sort of whipped scalable parallel data movement. We think we beat it for 20 years and it's pretty much hopefully dead. And so let's go after, well, let's add value to the data. Let's concentrate on metadata primarily. We talked about VPIC for a minute. VPIC is a particle in cell code. There's a trillion cells and a few million cells and a few trillion particles. And essentially, you run this application for a while. It runs, for weeks or something, and it's writing out these timestamps. And the timestamps it wants to write out is where was the particle at, which cell was it in, right? And it does this over and over again. So you think you're getting trillions of records every so often. It actually was written to write a file per particle per time step. So that's 1 trillion files per time step, which is fun for the metadata server. We decided that wasn't such a good idea, so we wrote a little library with Carnegie Mellon that made it think it was writing files, but it was really writing key value records into a parallel key value store that we had devised, running a few thousand copies of LevelDB. And it was pretty cool, right? So you're writing these records, it thought it was writing files, and then at the end it says, these 1,000 particles are interesting, and the first thing the scientist wants to know is, where were these particles at? Why are they interesting? So you could essentially just go in and do a query against it and come up with an answer, which was very neat. And so this is an example of how record-oriented store is likely to be in our future, which is very interesting because now I can say the word VSAM and I'll have really, truly come back around in my career for 30 plus years. Let's not go through that. Let's go to the next thing. The next thing is MDHIM. MDHIM is, okay, that was really easy because it was a single dimension index. All I wanted to know was where the particle was. What if I wanted to know not only where the particle was, but what was going on around it that made it be a fun particle? And so that implies more dimensions of index. How do you do a multidimensional index? at this scale, trillions of things, and you're trying to keep 3 or 4 dimensions of index against it. And so that's what MDHIM and XDHIM is about. It's a project going on right now funded by the Exascale Computing Project at DOE and DOD. And the kind of questions you want to ask yourself is, okay, well, how would I track a wave through time? And this is an AMR calculation, so you can see that different parts of the problem resolve differently, because you only resolve really tightly where the fun parts are, and where the unfun parts are, you don't care how tightly they're resolved. So you're running this application, you're doing these time steps, but how do you, but it can change. So every time step it'll look and say, well, you know what, the fun part moves, so I'm going to have to remesh this thing. And so how do you build an index when, that geolocates things when the geolocation is changing all the time? And so we thought about that a little bit, and we actually ended up borrowing something from Microsoft. There was a project called Farsight that essentially had this really cool concept of adding dots to the index, right, so that you can insert things in the middle. It reminds me of Fortran programming, adding zeros to the end of your column numbers. But at any rate, that's how the index works. So the index can grow and expand in various areas as you go, which is kind of interesting. And it actually is multidimensional. At current, it's 6 dimensions. But the whole idea is to be able to do things like track data through time. And then the last thing I'm going to talk about is, okay, we got all these file systems and all these storage systems, and they got all this damn trillions of metadata entries. How do you find anything at the laboratory? How do you find where your data is? And we started building this piece of software called Goofy, Grand Unified File Index. And essentially the idea is we want to try to cross a file system and a database. And so that's what we did. And the way it works is we replicate the tree, the directory part, but not the file part. And then we take the file metadata and we put a SQLite database at every node in the tree. And then we do very, very wide breadth-first searches that walk the tree in parallel, and very, very wide depth-first search, or breadth-first search threaded, and each one is doing an SQLite query, and the performance is just absolutely phenomenal. We've been totally amazed by it. So much amazed that on my little laptop there, that's actually a dual core, not a quad core, I built a thing with 250 million files, and I searched through the whole thing in 2 minutes. And it's way bigger than will fit in memory. I mean, it's way bigger. And so you're coming from a cheapo flash device on a little bitty old crappy 4-year-old Mac, and it goes this fast. Imagine how fast it would go on a real machine. We're actually buying a real machine to put it on, and we're hoping to be able to use this. This is also public domain, and you can come and get it. And I'm over time and done. That's not a picture of me, but I was actually there at that time. It's all public domain. It's all open source. I'm here the rest of the week. This is a great conference. Thank you for inviting me, and hopefully you enjoyed.
Gary, we have time for a question or two. There is one. Someone have a hand up? No questions? All right. Thank you so much, Gary. So next on the agenda is our break. So go out, have some coffee, refreshments, be back here at 10:40 for our next keynote with Adam Roberts of Western Digital.
So safe harbor, I can't predict the future. What I say is my opinion, and I could be wrong. So take that into account. This is what I think, and I'll tell you why I think it, and we can go from there. And hopefully there's some food for thought in here that'll can trigger wheels turning in your own mind. So really, we're on the precipice of just a new data center paradigm. When I came into this industry, as was said in the introductory words there, I started off as a pharmaceutical engineer. All my degrees are computer and electrical engineer, but I started as a pharmaceutical engineer. 2 reasons. There's a huge drug culture and community in Research Triangle Park, North Carolina, where I live. And 2, I started there as an engineer. And like ink and water, I spread into the chemistry aspects of it. 7 years in, I decided to step away from that and get back to what my degrees were, because it's really what I wanted to do. But I was shocked on day one as I stepped into my first role as a schematics guy in the world of computer design, because I was handed reference diagrams for how to wire things up. And I thought I just walked away from a pretty good pharmaceutical engineering job to do reference schematics. Like, what have I done? So I immediately started at that point, and I spent the next 18 years looking for the thing that would allow me to do something different. I met some of like these giants and legends of the industry at the time, or like I was involved in the days of the design of the first mouse or the first x86 server, and I'm like, wow, when am I going to get a chance to touch on something like that myself? Well, that came about when I stepped into the flash strategy in the early days. The first flash device I ever touched was, if memory serves me, in a development point of view, the first device was a 1 gigabyte flash device that cost several $1,000s, and you had to fill out paperwork as a chain of command as to who was in possession of it. It was like a piece of gold. Early days, and things have really, that's like a few cents now. So that was the first step. And the second step towards this, doing something that's new and different and having a chance to actually change the industry, I think is right now. This change in what's happening in the data center. And the idea is building a solution out of building blocks that's actually built to exactly what you need without over-provisioning, without having to pay for expensive software, and a surprisingly large amount of open source and open hardware designs being a part of it. It's surprising how well the industry's come together to allow this stuff to happen. So first, we'll talk a little about the history and why it's happening and the perspective behind all this. The core behind growth of computer really started as we stepped into the SAN. So SANs are great. SANs are expensive. SANs allow you to do some things you couldn't do before. Large capacity, sharing, but it was complicated, very expensive, still very expensive. Proprietary hardware and software for the most part. Management forces a lot of vendor lock-in. It's not the world of open hardware that you're seeing today. It's difficult to administer. Some people will stick with a SAN technology that they've been using for the last 10 years simply because they've got people with 10 years, 20 years experience on this space, and it's complicated to switch to someone else's. So in a lot of cases, maybe you need your own separate fiber channel network, things of this nature to make this happen. So there's some issues. And a lot of this, when things happen in the industry, it's usually the result of some pain. And what you see right now with DAS, and to some extent as people moved to NAS type designs, it happened because of the expense of SAN. Matter of fact, you could make the argument that the first large capacity SSDs was an opportunity for people who had, we'll say, moderate capacity needs tied to small compute needs that were forced into a SAN simply because they couldn't get the capacity in the box. And so we start giving them 4 or 8 terabyte SSDs and allow them to pull off of a SAN and save money. So NAS is a similar story. People step into NAS because, well, it's cheaper than SAN, and I can give up some of the SAN type overhead and some of the features. And one of the things about SAN that's great, but it's also problematic is the way it's designed, everything has to be bulletproof because it's the be-all, end-all of your data center or of your solution. And when everything's bulletproof, that means every I/O cache is mirrored, every wire is mirrored, every path is mirrored, every RAID controller was mirrored, everything was double, and it was very complex to test, things of that nature. NAS did away with a lot of that and was simpler and covers, everything's a shade of gray. Nothing I say is going to be this solution works for everyone. There's always the exception to the rule and sometimes multiple exceptions. But NAS is another shade of gray that works in some cases, but in other cases does not. And some of the cases where it did not, and you can't cover with a SAN or NAS, you'd spill into DAS and you see people, in the early days of online backup, you'd see people who'd take a compute box, an x86 box. They need almost no compute for the online backup stuff. You have some type of RAID engine, and then you'll cascade a bunch of DAS boxes off of it. Very cheap, run RAID 6 or whatever in the early days. You just run simple RAID instead of erasure code. You'd cascade a bunch of stuff together. And this is great in applications like that, but in other applications, if you're building a mission critical box, in my previous life as a solutions guy, an OEM for server design, one of the things I would see was almost every customer. This is a rule of thumb, but a rough rule of thumb, 60 to 70% over provisioning on anything that was business critical. The idea, even I worked at IBM, System X was the lower end of the brand, but even business critical inside IBM, rough rule of thumb I would use was 60 to 70% over provisioning. The idea was, this box is going to run for 5 years. I don't want to ever really take it down. I need the processors in it today that are going to be needed 5 years from now. So you're going to pay for those processors today. You're going to pay for that memory today. And anything else in that box that needs to be in there, you'd pay for it. And the non-mission critical was somewhere less than that, 30%. You know, rules of thumb. It varies from customer to customer, but I could almost count on certain ranges for certain customers, with mission critical being 60 to 70%. Interestingly enough, Ericsson did an economic study of the hyperscale data center, I believe it was a year or two ago, and in their study, they came up with 60 to 70%, which was exactly what I was using as a rough guide 10 years ago. So I felt somewhat of a relief to see that the numbers were staying steady, because when things change, it's really hard to track what people are doing. But it appears, from what I've seen, that things are still staying in that example of building a DAS-type box, that people over-provision way more than they should. So you can do virtualized DAS, and keep in mind, almost everything I've said now has been storage-focused. I'm going to spill into the idea of compute shortly. So in the case of virtualized DAS and virtualized machines inside boxes, this works to some extent. You know, if you think about what a typical server vendor will provide, you'll see three flavors, none of which quite fit anyone, but you can't have 1,000 SKUs. So what you'll have is the entry, the mid-range, and the high-end. And most people who do virtualized machines will build something with a high-end box. And for the same compute cycles, you pay more for that piece of hardware because it's more complex. You've got a bunch of NUMA stuff going on. You've got the ability to tie boxes together into multi-node. And this all has to be tested, and it all has to be guaranteed to work, especially considered that's the space where people tend to run mission critical. And as a result, for the same CPU cycles, it costs more. That's well and good, but it costs more. And then you wrap complex software around it, and you get something that costs even more. In some of these cases, I'll see solutions where 80% of the solution cost is software. This is a really, really big deal when you build solutions that has, say, 60% more compute than you actually need built into it, and you're paying licensing for software on those cores, but the cores are running at 20%. It's kind of wasteful. So how do we fix these things? It's really complex, because one, the thing that engineers in general don't take into account, but they need to, is human nature. People won't change unless, number one, there's enough pain involved in the solution that they're forced to change, because change is risk. Risk can get you fired. Risk can ruin your company. So you've got to take the human nature into account. That's the first thing. The second thing is change never happens as fast as people think it's going to happen, because nobody rolls out things by the day. No one decides today. No one comes here and hears something that I say, and tomorrow they're running it. Everyone has cycles. Maybe your next cycle to roll out new hardware is a year from now, maybe 2. So it takes time. So it's kind of funny. You'll hear someone say, maybe it's just a headline grabbing stunt. They'll say something like, hard drives are going to be done in 2 years. Tape is going to be done in 2 years. No, it's not. It's not. It's not. In 2000, I remember, in the year 2000, I remember having a conversation with my colleagues about the imminent death of fiber channel. And we're 2018 and it's doing pretty well. These things don't die. There's always someone who holds on. So just take that into account. Take nothing away from what I say here, that next year everything is going to be composable infrastructure or rack scale infrastructure. It just doesn't move at that rapid of a speed. So what do we do? So first off, I'm defining a term here, software-defined storage. 1.0 was really the attempt for people to emulate what hyperscalers were doing. Hyperscalers went out, bought a bunch of hardware, made it all look exactly the same, wrote custom software to run on that, and made it work. And a lot of people said, wow, they're really, really efficient. That guy has a 2 square mile data center. That's bigger than my county. What's going on here? I can do that too, and I can make money and be efficient. But in the world outside of a handful of hyperscalers, you don't have everything in your data center that is exactly the same. Maybe you have HP servers, maybe you have some IBM servers, maybe you've got some Supermicro stuff, maybe you've got some Western Digital drives, some Seagate drives. It's different. And as a result, that one-size-fits-all piece of hardware wraparound just doesn't work. So let's try again. We'll say SDS 1.1. Converged infrastructure, and that's the idea of, well, your stuff is a little different from this stuff, but we'll specifically test that config just the way it's done in the world of hyperscalers, and we'll make that work. And it does work, but it requires lots and lots of testing and lots of compatibility testing and things of that nature, and finding of bugs. One of the things I find it interesting how personally, I don't understand how anything works after having gone through development cycles and seen the problems that get found. I lose all confidence in everything we're doing after living, when I was in development, everywhere I've ever been and every company I've ever been involved with or worked and partnered with, you go through these development cycles where 100 bugs, 200 bugs, 500 bugs are found. And at the end, when there's no bugs, you're like, well, where's the next bug? You're just expecting it to come out of the woodwork. But this is what happens. You take a piece of hardware that's completely qualified, 100% qualified, and you put it in your hardware, which is 100% qualified, and bam, there was 80 bugs. It's horrific, but that's, you know, developers are the unsung heroes. I've lived it, and the pain, getting something right to be able to ship it it's incredibly difficult. So you see these problems, and what I'm referring to is SDS 1.1, trying to make these different configs and test them and make them all work. The overhead is huge. So we're back to where we started. Well, let's move to hyperconverged. And the idea of hyperconverged, once again, I'm not going to predict the end of hyperconverged. Hyperconverged is going to be around 20 years from now. It is what it is. It's actually a halfway decent solution. The idea of building units that has the compute and storage and memory that you need in the box and using that as a building block. I think it's going to exist and do well in the idea of composable infrastructure, but it does have some problems. One, if you can't change the building block, you're going to over-provision it to some extent. Disparity in the life cycles of the different components in this box. As an example, you stick some flash devices in this box, you stick some compute in this box, you stick some memory in the box. 3 years from now, maybe the processors are a little long in the tooth, but the rest of it especially in the case of flash, most flash devices are faster than the vast majority of people that use them actually need them to be. You know, they're using them as an accelerator or a replacement for hard drives, and they're 500x faster, and there's lots of leeway, but maybe something else gets long in the tooth. Well, there are companies out there that have like armies of young first-time engineers whose job is to take boxes apart and take out the pieces that are good and toss the rest aside. And it's a problem that's really difficult. And when you lock these things together physically, that's what you get, is people putting hands on servers. And oh, by the way, magically, when you take things apart, some percentage, 10 or 15% of the hardware never works again, strangely. You take it apart, put it on a bench, you put it back in, it doesn't work anymore. These things happen when you start tearing things apart in construction mode. So usually hyperconverged is proprietary and expensive, and scaling is weak in the space. So even there, still problems. So what do we do? Well, let's start to identify the problems. And the things I've been saying, it probably sounds like I'm just knocking every single thing we've done in the industry up to this point, but I'm not. Every one of those are good solutions, and they've served their need, and they're not going anywhere. But they have weaknesses that allow room for improvement. And so that was my attempt at identifying the problems. And now let's actually fix them. What pain points that sent us down this SDS path? Well, I'll refer to this as SDS 2.0. And after I finish a couple more charts that are storage-centric, I'm going to spill away from storage a little and start talking about the solution in and of itself. And I'm going to do that for a specific reason. Too often when you're in the silo of compute or in the silo of storage, you forget about the other half. And anytime you build something that's going to be composable or rack scale, anything in this fabric type world, you really need to be taking the other half of the equation into account. If you're not, you're building a SAN. You know, in the world of SAN, everything you do is concerned with what the storage does. And then you send things out on a fiber channel network and you have no idea what's going on the other side. And a solution like this needs to be a little more homogeneous. You have to actually be taking into account what the other side is doing. And that's what's happened here with things like Redfish, Swordfish, and even Western Digital's own Kingfish. These things are designed for allowing compute and storage to be managed with common tools. And this barrier between the two is being broken, and that's really what's needed to build true fabric type solutions. So we want pooled SDS that meshes well with pooled compute. That's the number one thing. We don't need a paradigm for storage and a paradigm for compute. The two need to mix. Think about the world of what goes on inside of hyperconverged. Everything is in the box. People manage those boxes with IPMI. People don't even know what IPMI is, and they're using IPMI. It's just ingrained in the solution as a part of it. So as this is replaced with something like Redfish, Swordfish, now you have Redfish for compute, Swordfish for storage, and as I mentioned, our own inside Western Digital is solution for managing is Kingfish, which is just an offset of Redfish, Swordfish. These things allow for homogeneous management and control, so you don't have to have these multiple silos and multiple ways to manage things, because it becomes very difficult to move forward. So you want standard protocols for accessing these things. You want really, really robust, reliable network. If you're going to put things on a fabric, you've got to have something that's designed for scale. And you really want a single network. You don't want some fiber channel network for storage, Ethernet, or whatever you're using for something else. And you want something that'll run both. Best of both worlds, the scalability of the SAN with DAS-like performance. And that's what we'll talk a little about. So problems we face. Data centers have these bottlenecks based to this unbalanced hardware that I talked to earlier. If you're building with a 50 or 60% over provisioning, which let's be clear, the hyperscalers are not, they're efficient. But everyone else is inefficient. I shouldn't say everyone else. A large portion of the rest are inefficient, and they're trying to move. No one's going to be as efficient as a hyperscaler without building to that scale. Scale adds efficiency in and of itself, but you want to approach that as best you can. So these DAS connections have been seen as the only way to pull this off, but there's opportunity here because we're doing things with our DMA that's adding, we'll say, 8 microseconds to the overall solution. So if I can put things on a fabric and mix the ratios that I need together as I see fit, and I can do that with, say, 8% hit overall with respect to the latency, that's kind of sort of a rounding error for a lot of it, for what you get for the efficiency. So those are the things we're going after. So let this be said, there's always an exception to every rule. There's a lot of people who won't need RDMA. in the world of, say, social media, the idea of social media, pick a company, you've got an account, you've got 1,000 friends. Those 1,000 friends are scattered over 100 countries. You post something, it's going to all of them. It's impossible for a social media company to control the locality of the data and have all your friends' data on one server because they're all tied to people, each one of them to another 900 friends. So it's impossible. So the structure of something like that is going to be built on the least common denominator, which is going to be internet. And so it doesn't matter if inside the rack I can get you down to 8 microseconds. Those solutions are going to be built in a different way. No, I meant Ethernet. I meant wide area network. I'm talking people in North Carolina talking to someone in China. I mean, who knows what you're going through when you make a pass like that? It's 100 milliseconds, 150 milliseconds. It's a long pole that. So inside the rack, maybe if you're at some social media company and this rack has 2 of my friends, but the other 898 of them are in another country, it doesn't really matter. So I bought nothing but the idea of RDMA in a case like that. So that's the point I'm trying to make there, is just the locality of the data. There's no control over it, really. So there's different flavors for everyone. So that's what makes this so complicated. Nothing is going to be a one-size-fits-all. And none of these solutions are going to die, but there's a new one being born here with the idea of the fabric and composable infrastructure. So in the DAS configurations, we really want to disaggregate storage and compute. And as I pointed to earlier, here's why. You build a server. See, I'm starting to speed up a little bit. I'm looking at the clock. So growing pains inside the server, this is what I need. I need some network, I need some CPU, DRAM, some SSDs, maybe some HDDs. I'm an SSD guy, so I didn't put any HDDs on this drawing. But I do work for a company that makes HDDs, so let's just pretend a couple of those are HDDs. So there's HDDs in there, we've got this solution, this is what we've got to deal with. But I end up building this. I've seen it, I've helped customers when I was in the world of selling servers. I built this for customers. I helped them. We'd lay out solutions that were over the top. And I knew they were over the top, and so did the customer. But this is what they had to do because they're like, I'm not opening this box for 5 years. I need this to be bulletproof, and I need it to have what I need by my projections for 5 years. So this is what we built. Well, this is kind of wasteful. I mean, but this is what we had to offer them, and this is what they wanted. So this is what they got. So let's not forget about the growing pains of the virtualized world and what happens with these migrations. We'll talk about this a little bit. So the idea is if you build a virtual machine and you actually get around, so I would say, do you want to go with a virtualized solution? Maybe you get a yes, maybe you get a no. But if you go with it, the idea is you put enough VMs or VDIs, whatever you put in there, the idea is to go from 20% utilization in that box today when you install it to something closer to 100%. You're not going to get 100%, but let's say you get close. We'll say 95%. If one of those VMs, whether it's a cloud burst type growth, maybe it's just growth over a period of time, or maybe this VM just needs more than what you can give it for today, you can go into most web services and change the amount of resources that are tied to it pretty much by the hour and just change these things. But if it grows too big to fit in this particular box, it's got to be migrated out. So if you think of the idea of cloud burst and you think of the idea of rapidly growing and changing resources like a living, breathing organism, if you're really close to 100% utilization, which is where you want to be for efficiency, the growth itself causes migrations because it won't fit on the box because the box is full, so you got to pull it out. So there's a bandwidth give and take as the tide flows. And this is a problem in and of itself because you're moving things back and forth. Maybe it shrinks and you want to put it back. You've essentially, it's like defragging a hard drive. Kind of sort of similar, but it's a data center. It's a defragmenting of the data center, moving things back to a more, so once again, once it shrinks, you're pulling it back, trying to be efficient again. So it's inefficient to some extent in a case like this. But in the world of composable infrastructure, you simply add another node. having spent enough time in my life dealing with solutions that are started on a lab where we're taking a soldering iron and tying pieces together, I think of it as a lab bench setup. You know, you've got a bunch of pieces, you tied them together, they're physically tied together like a DAS type config, and they operate like that, so you skip the need for expensive virtualized software, but they're logically tied together. You know, you go in with, if it was Intel, it would be a pod manager. If, you know, there's lots and lots of solutions out there, which I don't have enough time to talk about them all, but there's interesting discussions to have about several of these. You use this software, you tie some pieces together, and now you've got something that's been logically tied together. It's not virtualized, it's really hardware tied together, and it behaves more like it. So DAS doesn't really work, and for a number of reasons. It works for some people, but for others it doesn't, because this is expensive. What can we do? So the first thing that we have to do outside of the pieces is change the network. Now we know a big push coming from an SSD background, an HDD enclosure, if you're actually trying for performance of any kind whatsoever, you're probably not going to go above a 2 terabyte hard drive if you want performance. There's plenty of room to sell 8 and 10 terabyte hard drives. But if you're looking at performance and anything that you might consider an SSD for, you're going to do 2 terabytes or less. And the density is pretty low. And you move into SSDs, it goes up. But as we move into these new form factors designed specifically for flash, like the EDSFF stuff, the short and the long, I can get 8 of these where 2.5 inch drives go. And in the case of the ruler, it's really longer. You can put a lot more capacity on there. And the densities go up really high. The densities go up really high, causes all kinds of weird issues with a need to balance what's going on in the data center. So you need more network. So couple this with hard drives are much slower than SSDs. And if you look on the right side of the chart, HDDs and SSDs, the amount of overhead that's consumed in the solution overall with an SSD, a lot more of it is network. Hard drives are so slow, the network doesn't really play a portion. So once you get down in this space, and I'm looking for what I'm going to do with building the network, I really need something faster for those who want to do RDMA, want to do things of this nature. So you start building the solution, and you start looking at where the overhead is, and NVMeOF comes into play. So the idea, if everything moves to NVMe, and we build fabrics, and I want to be very clear, you're going to see fiber channel, you're going to see some InfiniBand stuff, maybe there's some OmniPath stuff being worked on that I'm not aware of, but there may be some OmniPath stuff coming out there. All these are fabrics, but really if I'm targeting the bulk of people in the center, it's going to be a mix of non-RDMA and RDMA and NVMe over fabric, because all the EDSFF stuff is going to be NVMe. That's the trend where the stuff is going. So protocol, I rip out SCSI, SAS stuff, I replace it with NVMe, and so I've made the device protocol better. I come at the network level, I rip out the SCSI layers, the TCP layers, replace it with RDMA and NVMe, and I make things a little more efficient there. Change these things. You need bandwidth on the devices themselves. You know, I was just talking about how bigger devices and more devices in a box, which come as a result of the EDSFF stuff, means all of a sudden I'm putting 12 by 8s or 12 by 4s, or maybe you'll have 36 EDSFF devices in a box. You need more and more bandwidth to actually take advantage of everything the device can do, which means lots of 100 gig links, or in some cases as we move on, you'll see 200 gig links and 400 gig links. These things will come into play. Everything affects something else. It's the butterfly effect here. The capacity of the devices affects the capacity density of the box. The capacity density of the box requires more bandwidth. More bandwidth means faster connections. If I'm using the box as a target and I'm burning CPU cycles in that box to do things with data, you move into RDMA to reduce that somewhat. So one thing affects the next, affects the next. So the whole idea of the network and storage latency being improved, you know, if you look at an SSD, as I showed on the other chart, the SSDs are so fast, a larger percentage of the overall transaction is getting consumed with network. So you see the left, well, we want what you see on the right, which is better and better network connections, which we're getting with the whole idea of RDMA coming into play and compute offloads. Compute offloads allow us to not burn cycles. There's a number of companies probably sitting in this very room that are producing network cards with 8 or 12 A72 ARM cores on it. And the idea is we move some compute down into the node. People who are building global RAID controllers running we'll say 4 enclosures getting ran by a global RAID controller in a RAID 6 type mode. What happens when there's a petabyte and a half in each of those enclosures and you've got to rebuild an enclosure in a RAID 6? You've been overwhelmed. So the idea of moving this stuff down into the box, this is where we start to see the effect of compute moving closer to the storage. The storage becomes so large that it becomes a gravitational force unto itself, where compute needs to move closer. And you'll see a breakup of host-based compute versus storage-centric compute start to happen as a result of these capacity points. The idea of putting a petabyte and a half in a 1U is real now, when it was ridiculous to even talk about something like that a year or two ago. But EDSFF and the smaller and smaller die that we're creating in the NAND world is making that possible. So, considering I'm getting really close to out of time, I'm going to speed this up a little bit. So, for any of this to happen, number one thing, and it's the thing I started on, one of the first things I said when we started, openness. It's surprising how well the industry has worked to provide open source type solutions. You're seeing things like Open19, OpenFlow, Open Compute Project. You know, the Linux Foundation's always been open, so is Hadoop. RISC-V, all these pieces are playing into one or another of these sensitive spots I just described in a way to provide something that will allow people to build such that you can have multiple sources. No one wants to build a 2 square mile data center and be tied to any one vendor who could go out of business or simply take the price up because it's proprietary. Everyone, at the scale we're seeing, everyone wants something that's going to be provided by more than one source. So it's really nice to see this come about. In the world of Fabric, the idea of what we want to see and what we're seeing happen is Fabric being built in a world where I provide compute elements, I provide storage elements. The compute elements are as simple as they can be so that they're as inexpensive as they can be. You tie them to simple compute bricks. You logically tie them together with some software package that you can get from a number of sources. They're not hard to find. You tie this together into a logically defined server. It behaves in a DAS-like fashion. If you need more performance, you move to RDMA. If you're doing something high-performance compute, maybe everything's tied together with an InfiniBand, whatever the case, and you build these solutions. So I really want to touch on compute slightly, and I've got 5 minutes. So let's jump down to compute. Point. So I'd mentioned a new control point. As we get more and more capacity in the box, there's a need to pull compute closer to the storage. Maybe you have a case where you're building things on a Fabric. You've got 5 2-petabyte boxes. Huge amount of database, and you want to do a query. Do you really want to move 10 petabytes back to the compute on the other end on the Fabric? Huge amount of time to do that, huge amount of bandwidth needed. So you start doing things like do the query locally and send the results back. It's not that much different than, say, what Hadoop does. When you look at a Hadoop node, it's not much difference, but this will spill over into more and more examples as we move forward. You'll see a lot of what's going on with big and fast data starting to intertwine. People have come to realize, I talk to companies almost weekly who say, wow, this data I've been piling away, there's value. I can run analytics on this and get real valuable information out of it. So you're starting to see people say, I don't want to be on tape, or I don't want to be on low-end hard drives. I want something that's maybe not the fastest thing on the market, but fast enough to allow me to do analytics on this data. Maybe I can sell the data, maybe I can use it internally to do my own thing. Now, one of the things I've talked again and again about storage, but I want to touch on this. It's an especially big topic inside my own company, is the idea of compute. And I think we're right now at maybe 1 billion cores a year, with a target of the next few years of jumping up to 2 billion cores a year. And we're a storage company. We're not even a compute company. The idea is big data, fast data are starting to spill over onto one another because of analytics and things of this nature. And in the world of compute, RISC-V is an opportunity for open compute and platforms that people can leverage without having to spill into licensed processors. And my own personal opinion, you're going to see all these processor types exist, and for a long, long time. But there's opportunities for spillover. One more example of an open hardware platform is the RISC-V processor. It's built to run big data fast. And memory-centric compute stuff, moving compute to the data, moving the processors closer to the data. I think you're going to see a bright future for RISC-V as well outside of storage. So, quick summary, and I think I'm out of time. I had 2 minutes. I'm right on. I had to skip a couple slides there, but I'm right on. I'm feeling good. So, summary. The fabric-friendly protocols, these methodologies, are really meeting individual pain points that are coming from specific customers. It won't meet everyone. Some people will still do SAN, some people still do NAS, but there's other customers who are trying to be efficient, getting away. If you've ever built, I'm sure there's someone in this room who's designed a solution that was 60% over-provisioned, and they want to get away from it without having to pay 80% of their solution cost being in some proprietary software. I've sold both. I've been involved in building both, and it's done, and now there's some opportunities for those who are doing it. Once again, if you can get by the human nature step of the risk and the pain and something different, there's opportunities to move off, and I think we're going to see a very bright future for the composable infrastructure, rack scale architecture type of brick-based solution on a fabric design. These large capacity points can be created. If you grow to some capacity point and you need some more, you logically assign some more. You don't have to over-provision to start with, and you don't necessarily need a SAN to do it. And the bricks in general, as you move to common bricks with open designs, you provide lots and lots of capacity from multiple sources, and you get the lowest cost, you get the most simplistic design, and then you add software layers on top. A lot of it's free. Some people do their own proprietary. And players like the virtualized world, these guys can still play in the space too. All this stuff still runs. Nothing's been architecturally changed to prevent you from running the same stuff you ran in older architectures on the new. And one thing, and I should have made this either the first bullet or the last, the TCA considerations on the design. You've got to take the software savings into account. Too often, coming from a world of storage, too often people are concerned with the cost of the storage device without taking into account the value of the device. If I can give you a device and it costs 5% more than what I gave you last year, but that 5% saves you 40% on the top end because you removed some software package or something else, you've got to take that into account and understand the whole picture, or you're never going to get anywhere. I frequently said, as I've tried to make progress in companies I've worked for, and this has been going on for 10 years. It takes patience to get where we are now. But I would say if the people who designed a bus engine only concerned themselves with the idea of engines, they would say, my bus engine costs more than a car engine. This is a foolish thing to build. I won't build it. But if you take into account the value it brings, maybe this costs 50% more, but this hauls 5 people and this hauls 100. You take that account, it makes sense to build the bus engine. And these designs, if you take into account top to bottom and the full TCA, TCO of the solution, these are fantastic solutions that I think are going to have great treadway. And I am finished. Thank you.
Thank you, Adam.
Thank you, Adam. Adam has assured me that he'll be here the rest of today and maybe even into the networking reception if you have questions for him. He likes those one-on-one confrontations? No, discussions? So we now come to our final speaker of this morning. I'd like to remind you, in case I forget, to please fill out your session evaluations that are available on the Smart app that you can download. And if you haven't done that, you can check out the code, snap code, over by the agenda that's on the monitor by registration. So finally, let's introduce Austin Donnelly. Austin Donnelly is a principal research software development engineer at the systems group at Microsoft Research in Cambridge. He's currently working on Silica, which is a project to store archive-grade data in glass. And previously, he worked on Pelican, a project that looked at cold storage for data center environments. Austin has worked on numerous solutions which have shipped in Microsoft products
I did not bring any.
with interesting names, from the Seaweed Project to Magpie to Ethernet topology and more. He obtained his BA in computer science from the University of Cambridge as well as his PhD, and we're looking forward to hearing him present on Glass, a new media for a new era. Welcome, Austin.
Okay, thank you very much for that. Very generous introduction. Can we get the mic sorted out, please? Okay, is that working slightly better? Good. All right, okay. So I realize that I'm the only thing standing between you and lunch, and it is a difficult position to be in. But I'm very confident that we have some exciting stuff to show you today in terms of the research that we're doing in storing data in glass. I'd like you to just take a moment and have a look at this picture. It looks absolutely beautiful. You've got these lovely rainbow patterns coming off that little triangle thing, the Azure logo. That's actually carved into the body of the glass using femtosecond lasers. And the little blue dots above it are tracks of data, many, many, many bits of data encoded in each of these dots through the physical volume of the glass. So today, I'll give you a quick tour of how we got to here, a little bit of background on some of the other systems that I've been involved in and how we decided that this was a good way forwards. So you've probably seen charts like this many times before. I haven't even bothered giving you the numbers on the axes. We have a lot of data. More and more data is generated. But the problem is that it costs a lot of money to store this data. So we can't afford to store all the data we would like to. And so really, with all of the projects that I've been involved in recently, what we've been doing is trying to reduce the cost of ownership of data so that we can get two different kinds of value from that. The first is kind of the obvious one. We can store more stuff. The second one is slightly more subtle, and it's that we can afford to keep data we already have for longer before we delete it. And so that's the second kind of value that we can generate. So when I say data, really, I'm thinking specifically of archival grade data. We've heard great talks about high-speed SSDs and NVMe and so on. I'm looking at entirely the opposite end of the spectrum here, stone cold data, data that would make tape look quite warm. So this is archival data, and to put a number on it, I'm thinking of an access rate of somewhere below a gigabit a second per petabyte stored. I think that's roughly where we see archive data is coming in. So this is a chart I quite like to show because it illustrates nicely the various technology options that we have today for storing our data. The bubbles are the technologies, and the axes are latency on the x-axis, and the data temperature that that technology is suitable for on the y-axis. So at the top left, you've got SSDs, which are rather expensive, but are a good fit for these very hot workloads. In the middle, you have various grades of hard drive, either performance hard drives or the much more popular nearline drives that are capacity optimized for lowest dollars per gig. And then right at the far end of the spectrum, you have tape, which has got excellent economics for bulk data, but unfortunately, we're looking at minutes to hours to access that data. So there's a trade-off between the workloads that you can support and the access latency. Now, notice there's actually quite a gap between what you can do with disks and what you can do with tape. So we initially looked at this gap and decided, well, what is it that we can do to fit in that space? And I'm going to give you a little bit of history about what the group that I come from, the Systems and Networking group in Cambridge, has been doing around these areas to fill those gaps. So initially, we started some of our storage research around 2007, doing some work on a technique that we called write offloading, where we realized that the speed of disks and the speed of networks had come to an inflection point where it was now cheaper to take a write request, send it across the network, and sync it to a remote disk within the rack. That was cheaper than going to your local disk if your local disk was contended. And so we built a system that allowed us to do this, to create artificially low load at particular disks in our rack so that we could then spin them down and get some power savings for that. And this was done in the context of RAID arrays. We also used a similar system to allow us to redirect these writes to handle peak loads, and that's a system called Everest that we built, where we could smooth out these peaks across a number of disks by moving the writes around, and that would allow us to handle higher peak loads with the same system. We also looked at SSDs that were becoming popular around 2009 and wrote a paper where we looked at the various characteristics of SSDs and compared them to the hard drives. And everybody at the time was telling us, oh, SSDs are great. You should move your entire workload to SSDs. They will take over the world. Well, you know what? Here we are, 2018, and there are many, many millions of hard drives being sold every year. They see no reason for them to go away. So having done that analysis, we were happy to publish that. Around the same time, we were also doing a bunch of work in rack-scale computing. In fact, we pretty much coined the term around this time frame, 2009. The CamCube project was a project looking at how we would put an awful lot of CPU nodes into a single rack and yet not have to have a rack's worth of Ethernet cables and many, many top-of-rack ports. And so we came up with the idea of using a 3D torus network to interconnect the systems within the rack and then be able to play with the amount of bandwidth within the rack versus the amount of bandwidth out of the rack. Now, later we kind of decided that merging these two streams of research would be something that would be quite interesting. What does it mean to think about storage at the scale of the rack? And so two projects came out of that, Pelican, which I'm sure some of you know about, and Silica, which was our glass storage project, which I'll tell you a little bit about more later. Now, notice there's a reasonably clear divide between the earlier work that we did based on RAID arrays and enterprise-grade servers and the kinds of things we're thinking of today, where we're looking at cloud-based technologies, where the minimum unit of deployment, the smallest thing we'll even bother thinking about, is an entire rack. The other difference is that in the past, the research that we did was very much focused on taking the ideas that we had and turning them into software. And that was the embodiment of the research. And if we could make a tweak to the software, that was good enough. That was interesting. But with CamCube, looking at rack-based computing, we realized that we would need to change the way that racks were wired. And so we started thinking about what does it mean to do research where we use software to compensate or take advantage of some of the special resources in the rack. And with Pelican and Silica, we've continued this trend where we've gone on further, integrating down the stack. So with Pelican, we started integrating with custom electronics design and the rack elevation, saying this is what the rack's going to be, and the software will be in charge of the entire rack. We also looked at working very closely with hard drive vendors so that we could understand how those devices worked, and we could take advantage of their capabilities. And then in the context of the Silica project, we've gone even lower to include basic physics, and we've now in fact hired some physicists to work with us so that we can understand the capabilities of the media, the glass, what we can do with it. And so now we're able to build these systems where we do these very large integrated co-designs where we consider the architecture of the system, the software at the top, through to the hardware components, the electronics, the mechanics, and the basic physics of the media behind it, all as one unified set of innovation. And I think that's one of the great skills of doing research in this multidisciplinary environment that we've managed to build over the number of years at Cambridge. So today I'm going to focus on two of those projects, Pelican and Silica. Pelican to give you a bit of context on where we are on cold storage, and Silica because that's the exciting stuff you've all come to hear about. So first of all, Pelican. So Pelican was a low-cost, is a low-cost hard drive-based archive system. So by that I mean we're targeting specifically cold workloads, and we're trying to build the cheapest possible system to store those cold workloads in a data center setting. So Pelican sits firmly in this particular part of the technology space. It's faster than tape, but it's lower cost than even capacity hard drives. So what is a Pelican? Well, it's 2 servers, and we take their PCI buses and we stretch them out across the entire rack to connect together 1152 standard 3.5-inch SATA hard drives. The cooling for the rack is vertical, not front to back as you would normally imagine, which means the entire rack is a single deployable unit. You can't service individual bits of it. The whole thing is one single unit. That's, the cooling being vertical is a good thing because if you think about the physics of the situation, warm air rises. This is the way the air wants to go. So it doesn't take very many fans to move the air around the system. So you build a system with very few fans. In fact, these 1152 drives are cooled by only 3 fans. Now, if you think of any other enclosure-based system, that's a ridiculously low number of fans to have in the system. So we have a number of constraints on the resources. I've talked about cooling, but power also goes in a different direction. It goes vertically in these trays that you can see in the system. And so we need to manage these constraints on how many drives we can spin in a power domain and how many drives we can spin in a cooling domain. All of that needs to be managed by software, and the software needs to have a holistic picture of what's going on in the rack. So you can't manage this as just individual little horizontal for you high storage sledges. You must manage this as a single unit. And so we built the software to do that. And that allowed us to take a huge amount of cost out of the system because there's basically nothing in this rack other than the hard drives and the bare minimum equipment to connect them into the data center network in a useful way. So whenever I give a talk on Pelican, there's always a handful of questions come up. One of them is, well, all these spin-ups and spin-downs on the disks, doesn't that ruin the lifetime of the disks? What does that do to your latency and performance numbers? So we work closely with drive vendors on these 2 points, and I can show you a small number of results on what that does to disks. And if you want more, then have a look at the published literature on Pelican, where you can see detailed analysis of that. The other thing we noticed was that having 2 servers connected to all of these disks, the reason we have 2 servers there is because you don't really want to have all of those disks behind one single server, because that gives you a single point of failure. And you don't want to be able, you don't want to lose access to all that service if you, all that storage if you lose the server. So we designed the system to allow us to migrate disks between the 2 servers so that we would always have access to our data, regardless of which of the servers was up. Maybe one server was down for monthly patching or something. So let me talk a little bit about archive drives. I'm showing you here a couple of pictures, one from Western Digital, one from Seagate. My point is that all of the main hard drive vendors offer archive hard drives. They are hard drives optimized to reduce cost. And the flip side is that they are not necessarily rated for 24/7 operation, which means if you try and use these drives in a standard RAID array, they will fail far faster than you would expect them to. So the only way you can consume these sorts of drives is in a Pelican-style system where you use the software to carefully manage the workload that those drives see. So they're targeting specifically the cold workloads. And in fact, there's a quote from the Western Digital data sheet for one of the drives saying, it's write once, read rarely, if almost never. Now, you can think of workload along a number of axes. Terabytes per year is a good way of thinking about it. So that really gives you a handle on the lifetime of the drive. The lifetime is also affected by things like the number of power on hours, how many hours is the drive turned on but not necessarily doing anything. It's affected by the terabytes transferred, as I've said, and also the spin-up, spin-down cycles. So we benchmarked a number of drives from different vendors. This table, I'm showing you the vendors are the alphabetic letters A, B, C. We worked with 3 different vendors. And the numbers are particular products from those vendors. They are anonymized for obvious reasons. We looked at PMR drives, we looked at SMR drives, hostware SMR, and autonomous SMR. And you can see that there's a variety of spin-up times from these different drives. So looking at the CDFs of these particular drives that we benchmarked, I'm showing you on the x-axis the spin-up time in seconds, and on the y-axis a CDF of how long we expect that population of drives to spin up. And there's really 2 key takeaways I'd like you to take from this chart. One is that these distributions are nice and tight. There's not a huge spread, and that's good because we want predictable spin-up times. The other is there's actually quite a large variation from manufacturer to manufacturer, and even from firmware revisions within a particular specific hardware platform from a single manufacturer. So some drives are spinning up in about 6 seconds, some a little over 10 seconds. That's quite a wide spread. In particular, if you look at the blue one with circles, that's B3V2. That's manufacturer B, drive 3, version 2 of the firmware. B3V1 is in gray. That's the same drive, but a different firmware load. You'll notice that's nearer 9 seconds. So you went from 6 seconds to 9 seconds for just a firmware change. So what's going on there then? Well, if you look at those drives, I've kept the colors the same, but if you look at the drives over time and the power they draw while they spin up, the left-hand side of the chart is a spin-up happening. You can see the current being drawn on the y-axis, time on the x-axis. The little up arrows here in color show you the point at which that particular drive completed its spin-up. And then the drives are quiescent for a while, and at time 18, we then send them a spin-down command, and there are down arrows showing when the spin-down is complete. Notice some of the drives, you send them a spin-down command, they still burn power for some time, in some cases several seconds before they spin down. And what was happening with these B3 V1 and V2 drives? Well, B3 V1 is here. Power draw goes up to a little under 15 watts, and then it drops. Whereas B3 V2 is up here. And this is why you're getting a faster spin-up, because B3 V2 is drawing far more power at the start, getting to its target RPM quicker, and then completing the spin-up. And that's entirely under software control in the firmware on the drives, which is why that sort of illustrates my point as to why we need to work closely with the drive vendors to get drives that are suitable for the systems that we build. So to remind you, Pelican fits in this particular space. The conclusion of the Pelican project was that we found the archive drives were useful, assuming that we were able to manage our workloads to the drives, and we are. We did a long-term study of drive reliability, and we published that elsewhere. You can go read the paper if you like. We found that the quick summary is that doing all these additional spin-ups and spin-downs does not affect the drive reliability. The drives that we were testing saw very similar annual failure rates to the drives in the rest of the data center. And truth be told, this way of using hard drives is the cheapest way of getting dollars per gig down for hard drive-based storage. So we've tuned everything we can. We've stripped out all the costs. What else can we do to get cheaper storage? Well, let's think about what we've got on the cards in terms of all of the media that we could play with. There's magnetic media, and here I'm looking at disk and tape. And we've got optical media. So disks use magnetic domains somewhere around 10 nanometers in size. The optical disks are much larger because they're typically operating somewhere around wavelengths, either a visible light or for Blu-ray disks towards the blue end of the spectrum. But ultimately, they are much larger feature sizes. And Blu-ray disks have got anything from sort of 4 to 8 layers. The data is held in the surface in a rather complicated structure of polycarbonate backing, thin layers, glue sandwiches. And the data is held on the surface of the disk, or very close to the surface on the disk. But really, the problem is that all of these technologies were designed before mega-scale data centers were around, and none of them have really been designed from the ground up to suit our needs. So I have a few examples here. So this is a hard drive. No surprises there. But I want to walk you through a few characteristics. There's a PCB on the back, right? Hard drives. Every hard drive comes with a read head, a write head, some media, and a PCB, a little bit of cache RAM in here. That's a single package. It's a non-negotiable unit. You buy everything. You get the same ratios of read and write, I/O bandwidth, and capacity. You can't change that after you deploy it. We would quite like to be able to change those ratios, but we can't. Tapes, and here I've got an example of a tape. Tapes are great. I love tapes. They're very, very cheap if you don't mind the fact they're quite slow. There's half a mile of tape in here, and it takes about 2 minutes to stream through this. So if you're unlucky and your file's at the end of this, minimum time to get to it, somewhere like 2 to 4 minutes. That's best case when there's nothing else in the system. But the way to get good costs with the tape system is to run them with very deep queues. And so there will be other stuff in the system. So you're not going to see 4 minutes to get stuff back from this. You're going to see hours to get stuff back from this. So like tape, like the economics, not sure I like the latency. Optical discs, so optical discs are nice, but they don't quite have the density. And they also have a worrying feature where they can either delaminate or the complex layerings can end up going quite milky. And I was speaking to some people in the movie and entertainment industry who said they tried doing backups to optical and had to stop after a few years because they realized they couldn't read anything they'd written. And that's not a backup technology in my book. And Flash, well, again, Flash is very expensive for these archive technologies. So really, is there a better media? I think you probably know the answer by now. So we think glass is a great media. Here I've got a little piece of glass in this jewel box, little 1-inch square, 2 millimeter thick. And this has got my slides from a talk I gave on this subject a little earlier. Come and talk to me after the talk if you'd like to see. I can show you the data actually shining in that bit of glass. So Silica is a project that we've started looking at long-term active archives. So long-term, by that I mean if it's data that you want to keep for over a year, maybe 10 years, maybe 100 years, for high-value data sets that you want to keep essentially in perpetuity. And by active archive, I mean faster than tape. I want to be able to look at this data from time to time. So why glass? Well, it's a great storage media. We store data in the glass by making permanent modifications to the structure of the glass. I'm showing you a picture of a clay tablet here. So why am I showing you a clay tablet? Well, this has got some cuneiform writing, and it's probably the oldest data that we have ever stored and successfully read again, and about 5,000 years old. This is actually currently in the British Museum in London. And some things never change. This is, in fact, recording the beer rations that were issued to some workers. But why has this survived? Well, they too have made permanent modifications to their media. They've taken a clay tablet, they've taken a reed, they've cut a point to it, they've made indentations, they've fired the tablet, and they've dropped it in the sand. We do not exactly the same, but we make similar permanent modifications to the structure of our glass using femtosecond lasers. Now, because they're permanent modifications, the technology is naturally a worm-like technology, sort of write once, read many. Or really, I'd like to say write once, read forever, because this is a very, very durable media. So this is an ideal fit for archival media. In terms of how long, when I say forever, I clearly don't mean actually forever. I mean multiple thousands of years, probably millions of years, based on some accelerated temperature-based testing that our colleagues at the University of Southampton have done. So what would you do with a media that you could keep for 1,000 years? What does it mean to store data more or less for free for 1,000 years? How would you use such a technology? These are all great, interesting questions. Of course, it's glass, so we don't need to worry about EMP or any of those sorts of things. If you're thinking of disaster recovery, then you do like these technologies that are not based on electrons stuck behind tunneling barriers or magnetic domains that are liable to sort of leak out over time. So it doesn't really suffer bit rot, which means that you can just write your data into the glass and leave it in place. I know of many people who run tape systems who realize that once the data is in the tape system, that's fine for 5, let's say 10 years, but at some point that tape system reaches end of life, and you need to buy the next generation, read out your entire archive, and write it down to the next generation of technology. And that's a non-trivial cost, both in terms of the time it takes to do that, the amount of data you're going to move, and as we store more and more data, it's a pyramid. There's a small amount of data we touch day to day, but there's a huge amount of data that's the archival data that we're talking about here. It has gravity associated with it. You really don't want to move that data if you can at all help doing that. And so putting it in glass means you don't need to move it. It's also very cheap. It turns out glass, well, it's just melted sand. So this is actually, at the end of the day, very, very cheap media. And unlike a tape, we can seek around this media. So really, glass gives us an opportunity, the permission, to re-examine a huge number of assumptions that we've had in the past around storage technologies. So what do I mean concretely by this? Well, for example, let's think about what it means to disaggregate the write capability, the storage media, and the read capability. I've already pointed out in hard drives, when you buy a hard drive, you're buying all three of those things in one go at a particular price point. However, yes?
Can you give a number, like cents per terabyte or gigabyte to go with your price as cheap?
No, not at this stage. We're talking to a number of glass manufacturers about those sorts of things.
But cheaper than tape?
I would imagine so.
You sound like Brett Kavanaugh.
I'm not sure that's a good comparison. So the nice thing about having media that's disaggregated from the read and the write head is that you can have a write system based on femtosecond lasers. You can then take your glass out of that, put it into a library system, think sort of tape library type thing. And then you can take it out of that and put it into a read system. And now you can scale that separately. You can decide how big to make your library area and choose the capacity that you need. You can choose the amount of write bandwidth that you provision by how many write heads you have. And you can change the amount of read that you have. And so over time, as your access patterns change, you can change your infrastructure to match. So why is glass now a feasible storage medium when it wasn't previously? Well, what's happened is that we are now able to take control of femtosecond lasers and use them. I'm showing you here two scan electron microscope. No, I'm not. I'm showing you two ordinary optical microscope pictures of, on the left, little spots that were written in glass using a picosecond laser. So a picosecond, the pulses are 10 to the minus 12 seconds. So quite short, but they're still delivering quite a lot of energy into the glass. And you can see there are these nasty black cracking lines that you can see there. This is no good for storing data. This is just too noisy. On the right, you've got a much cleaner picture where you're seeing these tiny little dots precisely placed, nicely aligned on a grid. And that was written using a femtosecond laser, 10 to the minus 15 seconds. For the pulses. And so using these high-speed lasers, we are now in a position to control the energy that's being delivered into the glass and to form these voxels, as we call them, to encode the data. So how do we actually do the writing? Well, we use one of these femtosecond lasers. We use the beam, focus it into the bulk of the material, and at the beam focus, when a pulse fires through a nonlinear multi-photon absorption mechanism, we get a voxel forming in the three-dimensional space in the glass that happens to be in focus. And what we do is we move the glass underneath the laser stays fixed, but the glass moves, and we write multiple voxels in a 2D layer that we call a sector, much like a sector on a hard drive. And then we move in the Z direction in order to get multiple sectors written in a vertical track through the bulk of the glass. Now notice, this is actually quite different from DVDs, CDs, and Blu-rays, where the data is held on the surface. But the data here is held in the bulk, and that's important because we're using the bulk of the glass to protect the data. So a small scratch on the surface or dust on the surface is going to be out of focus when you actually read it, and so you'll be able to read out the data from the bulk of the glass. So what do these voxels look like? This on the left is a scanning electron microscope picture of a single voxel. You can see there are these parallel plates that look a little bit like this. They're in 3 dimensions. They form a little sort of teardrop kind of shape. And this picture is a slice through the voxel. And it turns out that the angle of these plates depends on the polarization of the laser light that was used to make the voxel. And so if we can control the polarization, then we can control the angle of these plates. And so this is why we sometimes call this a 5-dimensional storage system, because we have the standard 3 dimensions of x, y, z of where we choose to place the voxel. We've got the direction from the polarization of the laser light to give us an angle. And we've got the amount of this, the size of this modification. You can think of the size of the teardrop giving us a 5th dimension, which is the retardance. And so that gives us our 5-dimensional. Now, you'll notice this is automatically a multi-bit scheme, a multi-level scheme, where depending on how many angles you can discriminate, you can encode multiple bits in the angles. So what does writing look like? Well, here I've got a picture of, hang on, I'm just trying to get the video to play here. There we go. OK, so this is mounting a camera looking directly down. The laser's pointing kind of into the screen. and you're seeing occasional flashes of laser light. That happens when the shutter of the camera is open while the laser happens to be firing. You see a little flash. And we've got the glass moving under the layer, under the laser. And we're putting down these little dots under computer control. And so this video has actually been slowed down a huge amount because otherwise you wouldn't be able to see the stage move. And we kind of joke in the lab that this is probably the world's most expensive dot matrix printer. So the next video I'd like to show you is how we read the voxels. So we use standard microscopy techniques to read out the polarization of these voxels. And so in this video, if I can get it to go. There we go. So you can see the picture of the microscope on the right, and here, this is the view that you can see from the microscope. You can see these two-dimensional sectors with tiny little dots in them representing the voxels. We can also focus the microscope through different layers in the glass, and that's how we read out multiple layers that are stacked on top of each other. So I mentioned we're doing polarization microscopy. What that really means is that actually we take 4 images for every sector that we want to read. This is what the images might look like at 4 different polarization states. And then from those 4 states, we do a little bit of linear algebra to compute a retardance, or how strong the polarization effect is, and the azimuth or orientation of the angle. And those two together, we can scatter plot them on a radial plot of angle, and the distance from the origin gives you the retardance. And so you can see these nice little clusters. We've got 8 clusters here, so we can discriminate between 8 different symbols. So this would be a 3-bit coding scheme. So in summary, glass is a great archive-grade material. It's got worm properties that we think are very important. It's seekable, unlike tape. It's quite cheap, and it has amazingly long lifetime. And so I think that glass is an excellent material for this kind of workload. Thank you.
Are you able to say something?
Yes?
Are you able to say something about read and write speeds?
Not at this time, no. So in general, I would make a comment that this technology is in its very, very early stages, and that I'm from Microsoft Research. I'm not making any product announcements. This is blue skies research, as you can tell. It took the hard drive industry about 40 years to go from a washing machine-sized hard drive to what you see today. So ask me the same question in 40 years, and I'll give you an answer. Yes? What kind of laser is it? Again, I don't want to say too much. Femtosecond pulsed laser. Sorry? I'm not actually sure. I'm not the physicist on the project. I'm the storage guy. Okay, yes? Sorry? Data density. Again, we are pushing density, but I don't really want to say too much about density because this is a very early stage project, and we're going to be working on that in the future.
So we are taking questions now.
Yes.
I know you're trying to jump the lunch line, but we are taking questions.
Okay, yes. Sorry. Yes. Yeah, so people should catch me over lunch. People should catch me over lunch if they want to have a look at my piece of glass. Yes. So it's a multi-bit. If you saw that little constellation diagram, is it a binary encoding or is it something else? It's a multi-level encoding scheme. So it comes down to how many angles we can discriminate and how many different levels of retardance we can discriminate. So if we are good at picking out different angles, then we can cram in more bits. Yes.
So, I think of, or I've been taught that glass is a super cool liquid. So does it change over time?
Yeah, so the question is, does glass flow? The question is, does glass flow? And some glasses do. If you look at old medieval churches, they're sort of saggy at the bottom. Technically, this is a different kind of glass. This is more like a crystal. It's a silica quartz glass. So this glass doesn't flow. But yes, some glasses do. Yes?
Back to the break, you talked about requirements related to high availability or reliability and data protection. Were there such requirements
Okay, so the question was about Pelican. I didn't talk about high availability or data protection or requirements. That's true. I mean, I can give you a whole hour talk on Pelican if you prefer. I refer you to our Pelican paper in OSTI 2014, but the quick answer is yes, these are very clearly important. We do use erasure coding to protect from failure of individual drives, and we use multiple head nodes to fail over for high availability. And if you're going to deploy it, at scale, then you would obviously want to spread your data across multiple racks to avoid from single rack failures. Yes.
Does this work kind of continue from things that, say, Enphase or others were doing, or like is the femtosecond laser kind of new versus what was going on 10 years ago or whatever?
So I'm not aware of what Enphase were doing.
I think they were doing holographic storage.
Okay, so we're not writing holograms here. We're making permanent modifications to the media. Holographic storage, as I understand it, the modifications are not permanent. You're trapping electrons in a higher energy state, and they may leak.
Okay.
Yes.
The dimensions of the media, and then secondly, the obvious one, what happens if you clock it?
Nothing. It bounces. So the dimensions, this is just a cheap optical blank you can get from any kind of optics supplier. It's a 1 inch by 2 millimeter size. I mean, it's good for us to experiment with. I'm fairly sure this is not the standard size we'll finish with. We still need to look at that in detail. There's a bunch of trade-offs.
Okay. Thank you so
Okay.
much, Austin. Thanks to all of our speakers, Adam, Austin, Gary, and Andy. And we're breaking for lunch now, and the breakout sessions will resume at 1 o'clock.